Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deep story of a wandering piece of ice that carries within itself the memory of our solar system's birth. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the cold reaches beyond Neptune, where sunlight arrives as little more than starlight, something ancient drifts through the darkness. The object measures perhaps a kilometre across, small enough to cradle in a city block, yet vast enough to contain multitudes of frozen time, its surface darker than charcoal and pocked with the gentle scars of 4 billion years, rotates slowly against the star-filled void. This is 3i Atlas. Though it bears no awareness of the designation humans will eventually give it, it simply exists, as it has existed. Carrying within its crystalline heart the molecular memory of a solar system's violent birth. The Wanderer's surface temperature hovers near absolute zero, where motion itself nearly ceases, and matter exists in states so rigid that glass becomes brittle as autumn leaves. Here, in this profound cold, water exists not as liquid or vapour, but as ice harder than granite. Carbon dioxide lies frozen into solid layers, and methane crystallizes into structures so delicate they would shatter at the touch of Earth's gentlest spring breeze. The comet tumbles in its trajectory, one face eternally dark, the other catching the faint whisper of solar photons that have travelled over 4 billion miles to reach this distant realm. Within the nucleus, locked in matrices of water ice, rest molecules that have not moved freely since the solar system's infancy. Carbon monoxide sleeps in pockets and veins, preserved like insects in amber. Molecular nitrogen, that most common component of Earth's atmosphere, lies trapped in concentrations that speak of temperatures so low they existed only in the earliest, coldest regions of the primordial solar nebula. These are not simply frozen gases, they are libraries of cosmic chemistry, archives of stellar processes that occurred when the sun was young and the planets were merely dreams of dust. The comet's journey began not here in the outer darkness, but closer to the sun, in the region where Jupiter's gravity now reigns. 4.5 billion years ago, when the solar system was little more than a rotating disk of gas and cosmic debris, countless bodies like this one accreted from the available materials. Some would grow to become planets, others would collide and merge, their substance contributing to larger worlds, but a precious few, including this wanderer, would be flung by gravitational encounters into the vast Oort cloud, that spherical shell of forgotten objects that extends nearly a quarter of the way to the nearest star. There, in Exile. The comet has waited. It has witnessed the birth and death of entire star systems in distant parts of the galaxy. It has felt the gentle gravitational tugs of passing stellar neighbours, each encounter nudging its orbit by imperceptible amounts. The cosmic background radiation, that faint afterglow of the universe's birth, has bathed its surface in photons older than Earth itself. Yet through all this deep time, the comet's interior has remained essentially unchanged, a time capsule preserving conditions that vanished from the inner solar system before the first stirrings of life began on the young Earth. The mystery that draws scientific attention lies not in the comet's existence. The Oort cloud likely contains trillions of such objects, but in what happens when one of these ancient wanderers begins its slow return toward the Sun. Most comets behave predictably as they approach the inner solar system. Solar radiation warms their surfaces, causing water ice to sublimate directly from solid to vapor. The release gas carries with it particles of dust, creating the characteristic coma and tail that have inspired human wonder for millennia. The process follows well-understood physics, and the chemical composition of the resulting outgassing typically matches what astronomers expect from objects formed in the outer regions of the early solar nebula. But 3I Atlas defies these expectations in ways that whisper of deeper mysteries. As it approaches the Sun, still far beyond the orbit of Mars, it begins to release not just water vapor and dust, but quantities of more volatile compounds that shouldn't exist in such abundance on a typical long-period comet. Carbon monoxide streams out in concentrations that suggest vast reservoirs preserved within the nucleus, molecular nitrogen, a gas so volatile it should have been lost to space billions of years ago, flows from the awakening surface in quantities that make astronomers pause and recalculate their models. The phenomenon challenges understanding in the gentlest possible way. There is no violence in this revelation, no sudden explosion or dramatic transformation. The comet simply continues its ancient trajectory while releasing molecules that carry isotopic signatures like fingerprints from the solar system's birth. Each departing gas molecule represents a small piece of evidence about conditions that existed when the Sun was surrounded by a disk of material waiting to become worlds. The ratios of different isotopes, variations of the same elements with different numbers of neutrons, tell stories of stellar nucleosynthesis and interstellar chemistry that occurred before the solar system existed. What makes this outgassing unusual is not just its composition, but its persistence. Long after the comet should have exhausted its supply of hypervolatile compounds, it continues to release these ancient gases. The phenomenon suggests that the nucleus contains materials preserved under conditions so extreme, so perfectly isolated from the warmth and radiation of the inner solar system, that they have remained essentially unchanged since the solar nebula's collapse. It is as though the comet carries within itself a sample of the primordial cloud from which all the planets, including Earth, eventually formed. The wanderer knows nothing of the instruments that will eventually study its composition, nothing of the scientists who will puzzle over its unusual chemistry. It simply follows the gravitational laws that have guided its motion for 4 billion years, slowly brightening as it approaches the Sun, slowly awakening from its deep cosmic sleep. In its gentle defiance of expectation, it offers a reminder that the universe still holds secrets, that even in an age of space telescopes and computer models, the cosmos can surprise us with revelations as subtle as an unusual mix of gases streaming from an ancient piece of ice. As it drifts through the darkness beyond the orbit of Jupiter, 3I Atlas continues its patient journey, carrying within its frozen heart the molecular memory of a time when the solar system was young and full of possibilities. The story it tells is written not in rock or metal, but in the delicate chemistry of ice and gas, a story that began before Earth existed and will continue long after our planet has returned to cosmic dust. The story begins not with the comet as it exists today, but with a disk of gas and dust rotating slowly around a young star that will one day be called the Sun 4.5 billion years ago. This stellar nursery extends far beyond where Pluto now orbits, a vast spiral of material still cooling from the gravitational collapse that ignited nuclear fusion in the central mass. The temperature gradient across this protoplanetary disk creates distinct zones of chemistry, each region favouring the condensation of different compounds based on their freezing points and the local intensity of stellar radiation. In the inner regions, where temperatures soar above the boiling point of water, only the most refractory materials can condense into solid particles. Silicate dust and metallic grains begin to clump together, eventually forming the rocky cores that will become the terrestrial planets. But farther out, beyond what astronomers call the snow line, water vapour begins to freeze into ice crystals that drift through the cooling nebula like cosmic snow. The addition of water ice to the available building materials dramatically increases the solid mass available for planetary accretion, allowing the formation of the massive cores that will capture hydrogen and helium to become gas giants. Yet even farther from the young sun, in regions where temperatures drop below 100 Kelvin, more exotic ices begin to condense. Carbon dioxide freezes out of the nebula gas at temperatures around 80 Kelvin. Carbon monoxide, that deadly yet cosmically abundant molecule, solidifies at even lower temperatures. Molecular nitrogen, so stable and unreactive that it dominates Earth's atmosphere, requires temperatures below 63 Kelvin to freeze from gas to solid. These hypervolatile compounds can only condense in the coldest, most distant regions of the protoplanetary disk, where the sun's heat arrives as little more than a distant whisper. It is in these outer reaches that the future three ices, Atlas, begins to form. The process starts modestly, with microscopic ice crystals adhering to tiny grains of silicate dust. Electrostatic forces and weak van der Waals interactions cause these particles to stick together when they collide, gradually building larger aggregates. The growing body remains porous, more like cosmic snow than solid ice, with vast networks of empty spaces that trap gases and preserve the chemical signatures of the surrounding nebula. As the protoplanet grows, its weak gravitational field begins to influence nearby material. Smaller ice particles spiral inward, adding their mass to the accumulating nucleus. The process operates with geological patience, millions of collisions over millions of years, each adding minor amounts of material to the slowly condensing body. The comet's composition reflects the local chemistry of its formation region, incorporating not just water ice but significant amounts of the exotic compounds that can only freeze at such extreme temperatures. The young solar system pulses with instability during this epoch of formation. The gas giants have not yet settled into their current orbits, and their gravitational influence sends cascades of perturbation through the remaining planetesimals. Jupiter, in particular, acts like a cosmic shepherd, its massive gravitational field scattering smaller bodies throughout the solar system. Some are flung inward toward the Sun, where they either impact the forming terrestrial planets or are destroyed by solar radiation. Others are hurled outward, beyond the gravitational dominance of the planets, into the vast spherical shell that will become known as the Oort cloud. The future three-eye Atlas finds itself among this latter group. A close encounter with the growing Jupiter, close in astronomical terms, meaning perhaps only a few million kilometers, alters its orbit sufficiently to send it on a trajectory that will carry it far from the sun's warmth. The gravitational slingshot effect accelerates the young comet to velocities that overcome the solar system's binding energy in its outer regions, launching it into an orbit so elongated that it will not return to the inner solar system for billions of years. During this violent ejection, the comet's internal structure preserves a record of the conditions that existed during the solar system's formation. The rapid cooling and low pressure of its formation environment create a matrix of amorphous ice, water frozen so quickly that its molecules cannot arrange themselves into the orderly crystal structures that form under more leisurely conditions. Within this glassy ice, pockets of hypervolatile compounds remain trapped, isolated from the vacuum of space by layers of less volatile materials. The preservation process operates with exquisite efficiency. Carbon monoxide, molecular nitrogen, and other hypervolatile compounds become incorporated not just as inclusions within the ice matrix, but as actual structural components of the comet's substance. The extremely low temperatures and pressures of the formation environment prevent these compounds from escaping even over geological timescales. The result is a body that essentially freeze-dries a sample of the early solar nebula, preserving molecular ratios and isotopic signatures that would otherwise be lost to the processes of planetary formation and evolution. As the comet settles into its new orbit in the Oort cloud, it carries with it information about the disk's temperature gradient, chemical composition, and isotopic heterogeneity. The ratios of different isotopes locked within its ice reflect the nuclear processes that occurred within previous generations of stars, the stellar nucleosynthesis that created the heavy elements necessary for rocky planets and organic chemistry. Oxygen isotopes preserve signatures of water formation in the cold molecular clouds that preceded the solar nebula's collapse. Carbon isotopes record the complex chemistry that occurred as organic molecules formed and were destroyed in the turbulent environment surrounding the young sun. The scientific mystery embedded within the comet's formation lies in understanding exactly how such pristine preservation could occur. Modern comets that have made multiple passages through the inner solar system show clear evidence of thermal processing and compositional evolution. Their surfaces become depleted in volatile compounds, and their interiors undergo structural changes that alter their original chemistry. Yet 3R Atlas appears to have avoided such modification, suggesting that its formation environment and subsequent history created conditions of almost perfect preservation. The puzzle deepens when astronomers consider the rarity of such objects. If the early solar system produced millions of comets with similar compositions, why do so few return with their primordial chemistry intact? The answer may lie in the precise timing and circumstances of their ejection from the inner solar system, or in subtle variations in their formation environments that made some bodies more resistant to modification than others. Each returning long-period comet represents a unique experiment in cosmic preservation, a test of whether the materials of the early solar nebula can survive the journey through deep time. As the newly formed comet begins its exile in the Oort cloud, it carries within its frozen structure a library of information about the solar system's birth. The carbon monoxide trapped in its interior preserves isotopic ratios that reflect the temperature and pressure conditions under which it condensed. The molecular nitrogen locked within ice matrices carries signatures of the stellar winds and radiation fields that influence the early solar nebula. Even the water ice itself, seemingly the most common component, contains subtle variations in isotopic composition that speak of the complex processes that governed volatile distribution in the protoplanetary disk. The irony of the comet's situation reveals itself slowly across cosmic timescales. Formed in a period of violent instability and rapid change, it has been preserved by exile in a region of almost perfect stability. The very process that removed it from the active solar system, gravitational scattering by the giant planets, has protected it from the thermal and chemical evolution that has modified every other body in the inner solar system. In its frozen isolation, 3I Atlas has become more than just a comet. It has become a time capsule, carrying within itself the molecular memory of an epoch when the solar system was young and the future remained unwritten. The gravitational slingshot that launches the young comet toward the Oort cloud operates with a precision that seems almost deliberate, though it follows nothing more than the inexorable mathematics of celestial mechanics. As the comet approaches Jupiter's sphere of influence, its trajectory bends under the giant planet's gravitational field, following a hyperbolic path that will fundamentally alter its relationship with the Sun. The encounter lasts only days in terms of closest approach, yet the accumulated effect of Jupiter's gravity acts across millions of kilometers of space, gradually accelerating the small body until its orbital velocity exceeds the escape threshold for its current distance from the Sun. The physics of this transformation unfolds with elegant inevitability. Energy and angular momentum must be conserved. So as the comet gains velocity from Jupiter's gravitational field, the giant planet loses an infinitesimally small amount of orbital energy in return. The exchange is so minute that Jupiter's orbit remains essentially unchanged. The mass difference between the planet and the comet spans 8 orders of magnitude. Yet for the small body, the encounter represents a complete transformation of destiny. What began as a roughly circular orbit in the outer solar system becomes a highly elliptical trajectory that will carry the comet to distances measured not in astronomical units, but in fractions of light years. The new orbital period stretches beyond human comprehension. Where once the comet might have completed an orbit around the Sun in decades or centuries, its new path requires millions of years for a single revolution. The aphelion, the farthest point of its orbit, lies so distant that the Sun appears merely as the brightest star in a field of stars, its gravitational influence barely perceptible against the competing pulls of passing stellar neighbours. At such distances, the comet becomes subject to galactic dynamics, feeling the subtle tidal forces of the Milky Way's rotating disk and the gravitational perturbations of nearby star systems. As the comet climbs away from the Sun, moving ever more slowly as gravitational potential energy increases at the expense of kinetic energy, it enters a realm of profound stillness. The turbulent environment of the inner solar system, with its stellar winds and electromagnetic fields, gives way to the near-perfect vacuum of the interstellar space. Here, matter densities drop to perhaps 1 atom per cubic centimetre, creating conditions of isolation so complete that the comet might travel for centuries without encountering a single dust grain of appreciable size. The temperature regime of this distant realm creates conditions unlike anything experienced in the inner solar system. Far from the Sun's warming radiation, the comet's surface temperature approaches the cosmic background temperature, the faint thermal remnant of the universe's birth. Now cooled by cosmic expansion to just 2.7 Kelvin above absolute zero. At such temperatures, molecular motion nearly ceases. Quantum mechanical effects begin to dominate over classical thermal behavior. The exotic ices trapped within the comet's interior achieve states of preservation impossible under warmer conditions, their molecular structures locked into configurations that will remain stable for geological ages. The journey outward reveals the true scale of the solar system's gravitational architecture. Within the orbit of Neptune, the Sun's gravitational field dominates all motion, holding planets and asteroids in relatively predictable paths, but beyond roughly 1,000 astronomical units, stellar influences begin to compete with solar gravities. The boundary is not sharp. There exists no clear demarcation between the solar system and interstellar space, but rather a gradual transition zone where the Sun's gravitational hegemony slowly yields to the collective pull of neighbouring stars. It is within this transition zone that the comet will spend most of its exile, occupying an orbital realm that astronomers classify as the inner Oort cloud, the outer Oort cloud, and all extending to perhaps 50,000 astronomical units from the Sun, contains bodies whose orbits are so weakly bound to the solar system that they can be perturbed by passing stars. The inner Oort cloud, sometimes called the Hills cloud after the astronomer who first described its dynamics, occupies the region between roughly 3,000 and 20,000 astronomical units, where comets remain more tightly bound to the Sun but still experience significant perturbations from galactic influences. The population of this distant reservoir challenges astronomical imagination. Conservative estimates suggest that the Oort cloud contains several trillion comet-sized bodies, with a total mass perhaps comparable to that of Earth. These objects represent the debris of planetary formation, the leftover building materials that escaped incorporation into the major planets. Their orbital inclinations span the full range of possible angles, creating a roughly spherical distribution around the Sun rather than the flattened disk characteristic of the inner solar system. The scientific mystery of the Oort cloud lies partly in its very existence. Computer simulations of the early solar system suggest that the process of planetary formation should have ejected most small bodies either into the Sun or completely out of the solar system. The survival of a substantial population in weakly bound orbits requires a delicate balance of gravitational perturbations, a cosmic choreography that preserves some objects while eliminating others. The mechanism appears to involve multiple encounters with the giant planets, gradually raising orbital energies until bodies reach the stable refuge of the distant cloud. Within this population, 3I Atlas represents something unusual, a body whose formation environment and subsequent history have conspired to preserve primordial materials with extraordinary fidelity. Most Oort cloud objects show some evidence of thermal processing or impact modification during their journey from the inner solar system. Collisions with other small bodies can alter surface composition and internal structure. Solar heating during the outward journey can drive off the most volatile compounds. Even cosmic rays, those high-energy particles that pervade interstellar space, can gradually modify surface chemistry over millions of years. Yet somehow, 3I Atlas has avoided significant modification. Perhaps its ejection occurred more rapidly than average, minimizing thermal processing during its passage through the inner solar system. Perhaps its interior structure, with particularly effective insulation between volatile-rich regions and the surface, has prevented the loss of hypervolatile compounds, or perhaps it represents one of the earliest objects ejected to the Oort cloud, formed when the solar nebula's chemistry was different from later periods of planetary accretion. The preservation mechanism operates through multiple layers of protection. The comet's surface, darkened by eons of cosmic ray bombardment and micrometeorite impacts, acts as an insulating layer that prevents solar radiation from penetrating to volatile-rich regions beneath. The extremely low temperatures of the Oort cloud environment ensure that even the most volatile compounds remain frozen solid, their vapor pressures so low that sublimation rates become negligible. The near-vacuum conditions eliminate convective heat transfer, leaving only the slow process of radiative cooling to carry away what little thermal energy the comet receives from starlight and cosmic background radiation. Within the nucleus, the original structure of the comet, that porous mixture of ice and dust that formed in the outer solar nebula, creates a natural preservation matrix. Trapped gases remain isolated within individual pockets and pores, prevented from escaping by the surrounding ice and dust. The amorphous structure of the water ice, frozen so rapidly during formation that its molecules could not arrange themselves into ordered crystals, provides additional stability for incorporated volatile compounds. The isotopic signatures locked within these preserved materials offer a unique window into the early solar system's chemistry. Different regions of the protoplanetary disk experience different thermal histories and chemical evolution, creating gradients in isotopic composition that reflect local conditions during planetary formation. The ratio of deuterium to hydrogen in water molecules, for example, preserves information about the temperature and pressure conditions under which the ice originally condensed. Nitrogen isotope ratios carry signatures of stellar nucleosynthesis and interstellar chemistry that preceded the solar nebula's collapse. As the comet settles into its distant orbit, following an elliptical path that will carry it slowly around the Sun over the course of millions of years, it begins a period of dormancy unlike anything experienced by objects that remain in the inner solar system. The thermal environment becomes so stable that temperature variations occur only on geological timescales, driven primarily by the slow evolution of stellar luminosity and the gradual passage of the solar system through different regions of the galaxy. The gravitational environment of the Oort cloud operates according to different rules than those governing planetary motion. Instead of the simple two-body dynamics that describe planet-sun interactions, comet orbits in the distant cloud experience perturbations from multiple sources. Passing stars can alter orbital elements over short time periods. Astronomically speaking, the galactic tide, the differential gravitational effect of the Milky Way's mass distribution, creates systematic torques that slowly evolve orbital orientations. Even molecular clouds encountered during the solar system's galactic orbit can exert measurable gravitational influences on the most distant comets. These perturbations ensure that the Oort cloud remains a dynamic system despite its apparent stillness. Comets that begin with stable or circular orbits gradually acquire eccentricity and inclination changes that can eventually send them back toward the inner solar system. The process operates with geological patience, requiring millions of orbital periods to produce significant changes in most cases, yet occasionally, a particularly close stellar encounter or passage through a dense interstellar cloud can dramatically alter many comet orbits simultaneously, creating periods of enhanced comet activity in the inner solar system. The irony of the comet's exile reveals itself in this dynamic stability, removed from the active solar system to preserve its primordial composition. 3a. Atlas paradoxically remains connected to galactic process that will eventually determine its fate. The same gravitational perturbations that maintain the Oort cloud's population will someday redirect the comet's orbit, sending it on a return journey toward the Sun. When that return finally occurs, after millions of years in the cosmic deep, the comet will carry with it a molecular library of the early solar system, preserved by the very exile that seemed to remove it permanently from the story of planetary formation. The comet tumbles slowly through the darkness, its rotation gradually slowing due to the minute torques exerted by solar radiation pressure and magnetic fields. In the profound cold and near-perfect vacuum of the Oort cloud, time itself seems to slow, measured not in days or years but in the gradual drift of stellar positions and the slow evolution of galactic structure. Yet within the comet's frozen heart, the chemical signatures of a violent and creative epoch remain perfectly preserved, waiting for the moment when gravitational dynamics will wake the ancient wanderer from its deep sleep and send it home. The Oort cloud becomes a realm of perpetual twilight, where the distinction between day and night loses all meaning and time flows like honey through the cosmic deep. Here, in the outermost suburbs of the solar system, 3R Atlas settles into a rhythm of existence measured not in rotations or seasons, but in the slow procession of stellar neighbours and the gradual drift of galactic arms. The comet's surface temperature stabilises at values so low that helium itself would freeze solid, creating conditions of preservation more perfect than any earthly laboratory could achieve. Within this thermal sanctuary, molecular motion approaches its quantum mechanical minimum. The hypervolatile compounds trapped in the comet's interior exist in states of near-perfect crystalline order, their atomic arrangements locked into configurations that will remain stable for millions of years. Carbon monoxide molecules nestle within cavities of water ice, held in place by van der Waals forces so weak that they would be overwhelmed by thermal motion at higher temperatures. Molecular nitrogen forms clathrate structures, cage-like arrangements where individual gas molecules become imprisoned within crystal lattices of other compounds, creating inclusion complexes that preserve both the guest and host molecules from chemical alteration. The preservation mechanism operates with a thoroughness that borders on the miraculous. Cosmic ray bombardment, that constant shower of high-energy particles from distant supernovae and stellar winds, penetrates only the outermost layers of the comet's surface. Below a depth of perhaps 10 meters, the nuclear density of the comet's material provides sufficient shielding to prevent significant radiation damage to the preserved organic and inorganic compounds. The result is a body whose interior chemistry remains essentially frozen in time, a snapshot of molecular ratios and isotopic signatures that date to the solar system's birth. The scientific puzzle embedded in this preservation lies in understanding how such delicate chemical structures can survive the violence of the comet's original ejection from the inner solar system. During its gravitational encounter with Jupiter, the comet experienced accelerations and tidal forces that should have disrupted its internal structure. The passage from the relatively warm environment of the outer solar nebula to the extreme cold of interstellar space occurred over a timescale of thousands of years, rapid by geological standards, yet potentially long enough for volatile compounds to escape through sublimation. Yet somehow, the comet's architecture proved resilient enough to preserve its molecular cargo intact. The porous structure that formed during its original accretion, with its network of interconnected cavities and channels, may have provided multiple barriers to gas escape. As the outer layers cooled and solidified, they formed an increasingly effective seal that trapped volatiles in the interior. The process resembles the formation of permafrost on Earth, where surface freezing creates an impermeable cap that preserves organic materials beneath, but operating at temperatures and pressures far beyond terrestrial experience. The comet's rotation gradually slows during its exile, affected by the minute torques exerted by solar radiation pressure and magnetic field interactions. What began as a rotation period measured in hours or days extends to weeks, then months, as the cumulative effect of these tiny forces extracts angular momentum from the spinning body. The slowing rotation creates even more stable thermal conditions, eliminating the day-night temperature cycles that might otherwise drive sublimation and chemical alteration. In the profound stillness of its distant orbit, 3i Atlas becomes a cosmic meditation on preservation and change. Its surface, bombarded by cosmic rays and micrometeorites over millions of years, gradually darkens and develops a protective crust of carbonaceous material. This weathered layer, typically only meters thick, serves as thermal insulation that further stabilizes the interior temperature. Below this protective barrier, the original ice and dust matrix remains essentially unchanged, maintaining the chemical composition and physical structure that formed during the solar system's youth. The orbital mechanics of the Oort cloud create a gravitational environment unlike anything in the inner solar system. Instead of the dominant central force of solar gravity that controls planetary motion, Comets in the distant cloud experience a complex interplay of influences. The Sun's gravitational field, though still the strongest single influence, must compete with tidal forces from the galaxy's mass distribution and perturbations from passing stars. The result is an orbital evolution that proceeds with glacial slowness but inexorable persistence. Stellar encounters provide the primary mechanism for altering comet orbits in the Oort cloud every few million years, on average. A star passes within a few light-years of the solar system, its gravitational field extending tendrils of influence that can reach the most distant comets. These encounters rarely result in dramatic changes. The closest stellar approach in the past few million years brought a star to within about a light-year of the Sun. Yet even such distant passages can alter the orbital elements of weakly bound comets. The perturbations operate through differential gravitational effects, with the side of a comet's orbit facing the passing star experiencing slightly stronger gravitational attraction than the opposite side. Over the course of the stellar encounter, these small differences accumulate into measurable changes in orbital energy and angular momentum. Most encounters result in minor modifications that leave comets in stable, if slightly altered, orbits within the cloud, but occasionally a particularly close approach or favourable orbital geometry can provide enough energy to send a comet on a trajectory that will eventually return it to the inner solar system. During its long exile, 3I Atlas experiences several such encounters, each leaving subtle fingerprints on its orbital evolution. A red dwarf star passing 3 light-years away nudges its aphelion slightly inward. A binary system, gravitationally bound stars orbiting their common centre of mass, creates more complex perturbations that alter both the comet's orbital inclination and eccentricity. Each encounter represents a roll of cosmic dice, with outcomes determined by the precise timing and geometry of the stellar passage relative to the comet's position in its orbit. The mystery of comet survival in the Oort cloud extends beyond mere orbital mechanics to questions of physical integrity and chemical stability. Computer simulations suggest that collisions between comets should be relatively rare at the low densities characteristic of the distant cloud, yet such encounters do occur over million-year timescales. A collision between 2 comet-sized bodies at typical Oort cloud velocities would release enough energy to vaporize both objects, destroying any record of their original composition and structure. Yet 3I Atlas appears to have avoided such catastrophic encounters, either through fortunate orbital geometry or perhaps through the statistical protection provided by the vast volume of space available in the outer cloud. The probability of collision decreases rapidly with distance from the Sun, as the same number of objects becomes distributed through an ever larger volume. At the distances characteristic of the inner Oort cloud, collision rates drop to values so low that most comets can survive for the age of the solar system without experiencing a destructive impact. The chemical evolution that does occur during the comet's exile proceeds through pathways entirely different from those operating in the inner solar system. Instead of thermal processes driven by solar heating, alteration occurs primarily through radiolysis, the breaking of chemical bonds by cosmic ray bombardment. High-energy particles striking the comet's surface create cascade showers of secondary particles that can penetrate several meters into the nucleus, gradually converting complex organic molecules into simpler compounds and creating new chemical species through radiation-induced reactions. Yet even these processes operate with geological slowness in the extreme cold of the Oort cloud. Reaction rates that might proceed rapidly at room temperature become almost negligibly slow at temperatures near absolute zero. The result is a body whose surface undergoes gradual chemical evolution, while its interior remains essentially pristine, creating a preserved record of the chemical conditions that existed during the solar system's formation. The isotopic signatures locked within the comet's ice carry information that extends far beyond the solar system's own history. The ratios of different isotopes reflect nuclear processes that occurred within previous generations of stars, the stellar nucleosynthesis that created the heavy elements necessary for rocky planets and organic chemistry. Oxygen isotopes preserve signatures of water formation in the cold molecular clouds that preceded the solar nebula's collapse. Carbon isotopes record the complex chemistry that occurred as organic molecules formed and were destroyed in the interstellar medium. As the comet continues its slow journey through the Oort cloud, following an elliptical path that carries it alternately closer to and farther from the Sun, over periods measured in millions of years, it maintains its role as a passive observer of cosmic evolution. The galaxy rotates around it. Stellar generations are born and die, yet the comet persists in its frozen orbit, carrying within its crystalline heart the molecular memory of an epoch when the solar system was young and the future remained unwritten. The irony of its situation becomes more apparent with each passing eon, preserved by exile from the very system whose birth it commemorates. It drifts through the cosmic deep like a message in a bottle, waiting for currents of gravity to carry it home, the gravitational nudge that will eventually return 3i Atlas to the inner solar system begins not as a single dramatic event, but as an accumulation of tiny perturbations spread across millions of years. A red dwarf star, one of the galaxy's most common stellar citizens, follows an orbit through the Milky Way that will bring it within 2 light-years of the Sun. The approach unfolds with astronomical patience. The star's motion relative to the solar system amounts to mere kilometers per second, yet across the vast distances involved. This represents a gravitational encounter of profound significance for the distant members of the Oort cloud. The mathematics of the interaction operate through what astronomers call the restricted 3-body problem, though in reality the situation involves far more complexity. The comet orbits the Sun under the primary influence of solar gravity, but as the passing star approaches, its gravitational field begins to compete with that of the Sun for control of the comet's motion. The perturbation develops gradually, with the stellar gravity initially producing only tiny deviations in the comet's trajectory. These small changes accumulate over thousands of orbital periods, slowly altering the fundamental parameters that define the comet's path through space. The orbital elements most susceptible to change during such encounters are the eccentricity and the semi-major axis, the parameters that determine how elongated the orbit becomes and how much energy the comet possesses relative to the Sun's gravitational field. Initially, through 3i Atlas, follows a roughly circular path in the outer Oort cloud, with an orbital energy so negative that it remains firmly bound to the solar system despite its enormous distance from the Sun. As the passing star's gravity begins to influence the comet's motion, this energy balance starts to shift in subtle ways. The perturbation mechanism operates through tidal effects, differential gravitational forces that act differently on various parts of the comet's orbit. When the comet lies on the side of its orbit facing the passing star, it experiences slightly stronger gravitational attraction toward the interloper than when it occupies the opposite side of its path. Over the course of multiple orbital periods, these small differences in gravitational acceleration accumulate into measurable changes in orbital velocity and position. The process unfolds with exquisite sensitivity to initial conditions, a comet that happens to be at aphelion. When the passing star reaches its closest approach, experiences different perturbations than one at perihelion during the same stellar encounter. The 3-dimensional geometry of the encounter The angle between the comet's orbital plane and the star's trajectory, the relative velocities involved, the precise timing of closest approach, all combine to determine the magnitude and direction of the resulting orbital changes for 3I Atlas. The encounter proves fortuitous in its timing and geometry. The passing star's gravitational field acts like a cosmic billiard cue, imparting just enough energy to the distant comet to alter its orbital parameters in a specific way. The semi-major axis decreases slightly, bringing the comet's aphelion closer to the Sun while leaving its perihelion distance essentially unchanged. The result is an orbit with higher eccentricity, more elongated than before, that will carry the comet much closer to the Sun during its next approach. The scientific mystery embedded in this process lies in understanding why some stellar encounters send comets toward the inner solar system, while others eject them completely from the solar system or leave their orbits essentially unchanged. Computer simulations suggest that the outcome depends critically on the detailed dynamics of each encounter, with small changes in timing or geometry producing dramatically different results. The phenomenon exhibits characteristics of deterministic chaos, systems where the long-term behavior becomes unpredictable despite following deterministic physical laws. The orbital transformation occurs so gradually that it would be imperceptible to any hypothetical observer traveling with the comet. The changes in velocity amount to mere meters per second spread over thousands of years. Yet these tiny alterations accumulate into a fundamental change in the comet's destiny. What was once a stable, nearly circular orbit in the outer Oort cloud becomes a highly eccentric trajectory that will eventually bring the ancient wanderer back to the realm of planetary influences. The new orbital period remains enormous by human standards, perhaps several million years for a complete revolution around the Sun, yet it represents a dramatic decrease from the comet's original period in the distant cloud. More importantly, the altered perihelion distance will carry the comet well within the orbit of Neptune during its next approach, bringing it into the gravitational sphere of influence of the giant planets for the first time in billions of years. As the stellar encounter concludes and the passing star continues on its galactic orbit, 3I Atlas begins its slow journey back toward the inner solar system. The return trip will consume millions of years, during which the comet will experience environmental conditions that gradually transition from the extreme cold of interstellar space to the relatively warm embrace of solar radiation. The transformation will not occur suddenly. There exists no clear boundary between the Oort cloud and the planetary region, but rather as a continuous evolution of temperature, pressure, and radiation environment. The comet's surface begins to respond to these changing conditions long before it reaches the orbit of the outermost planets. At distances beyond 1,000 astronomical units from the Sun, solar radiation remains too weak to drive significant sublimation of water ice, yet it gradually warms the nucleus above the cosmic background temperature. The dark radiation-processed surface layer that formed during the comet's exile begins to conduct heat inward, slowly raising the temperature of subsurface materials that have remained at near absolute zero for millions of years. The thermal evolution proceeds with geological patience, governed by the slow process of heat conduction through the comet's porous interior. The insulating properties of the nucleus, a consequence of its high porosity and the low thermal conductivity of ice and dust mixtures, ensure that temperature changes propagate inward at rates measured in centimeters per year. The result is a body whose surface begins to warm while its deep interior remains essentially unchanged, creating thermal gradients that will eventually drive the complex chemistry of outgassing. Within the warming outer layers, trapped gases begin to stir for the first time in millions of years. Carbon monoxide, with its extremely low sublimation temperature, starts to show the first signs of mobility, molecular nitrogen, even more volatile, begins to exhibit vapor pressures high enough to drive slow migration through the comet's porous structure. Yet these processes remain largely confined to the outermost layers of the nucleus, with the bulk of the comet's volatile inventory remaining locked in the frozen interior. The scientific puzzle of the comet's composition begins to reveal itself during this gradual awakening. Spectroscopic observations of other long-period comets have shown that such objects often display unusual volatile compositions compared to their short-period counterparts. The differences reflect the preservation environments experienced by these two populations. Short-period comets have undergone thermal cycling during multiple passages through the inner solar system, while long-period comets like 3I Atlas have remained essentially pristine since their formation. The isotopic signatures locked within the comet's ice begin to acquire new significance as the return journey progresses. These molecular fingerprints, preserved for billions of years in the frozen matrix of the nucleus, carry information about the chemical conditions that existed during the solar system's formation. The ratios of different isotopes reflect the nuclear processes that occurred within previous generations of stars, the stellar nucleosynthesis that created the heavy elements necessary for planetary formation and the eventual emergence of life. As 3I Atlas continues its slow approach toward the inner solar system, it carries within its ancient heart a library of information about the solar nebula's composition and evolution. The carbon monoxide trapped in its interior preserves isotopic ratios that reflect the temperature and pressure conditions under which it originally condensed. The molecular nitrogen locked within ice matrices carries signatures of the stellar winds and radiation fields that influenced the early protoplanetary disk. The return journey represents more than just a change in orbital dynamics. It marks the beginning of a scientific opportunity that occurs only rarely in astronomical terms. When a pristine comet from the Oort cloud returns to the inner solar system, it provides astronomers with a unique window into the chemical and physical conditions that existed during planetary formation. The comet becomes a time traveler, carrying samples of the early solar nebula back to an epoch when technological civilization has developed the tools necessary to decipher their molecular messages. The irony of the comet's situation becomes more pronounced as it begins its homeward journey. Formed in the chaotic environment of the early solar system, then preserved by exile in the sterile cold of the Oort cloud, it now returns to find a solar system transformed beyond recognition. The planets have settled into stable orbits, their surfaces shaped by billions of years of geological evolution. On one small rocky world, life has emerged from the same chemical elements that comprise the comet's nucleus, eventually developing the cognitive capacity to recognize in the returning wanderer a messenger from their common cosmic birth. The first stirrings of awakening occur at distances so vast that Earth appears merely as a pale blue dot lost in the sun's glare. Yet already the ancient ice begins to respond to the gradual increase in solar radiation. At roughly 50 astronomical units from the Sun, still beyond the orbit of Pluto, the surface temperature of 3I Atlas rises above 50 Kelvin for the first time in millions of years. This seemingly modest warming, barely detectable by the most sensitive instruments, triggers a cascade of subtle changes that herald the comet's transformation from dormant wanderer to active celestial body. The physics of the awakening process operates through mechanisms that remain partially mysterious even to contemporary astronomers. Solar photons, arriving after their 8-hour journey from the sun's surface, strike the comet's dark nucleus and deposit their energy in the uppermost layers of ice and dust. The comet's low albedo, a consequence of millions of years of cosmic ray bombardment and space weathering, ensures that most of this energy becomes absorbed rather than reflected back to space. The absorbed radiation gradually raises the temperature of surface materials, initiating thermal diffusion into the interior. Yet the process proves far from uniform or predictable. The comet's irregular shape and rotating motion create complex patterns of heating and cooling that vary with latitude and local topography. Regions that face the sun directly experience the strongest warming, while areas in permanent shadow remain at temperatures close to absolute zero. The boundary between these thermal regimes creates steep temperature gradients that drive sublimation and gas flow in ways that challenge theoretical models of comet behavior. The first gases to respond to the warming are the hypervolatile compounds that require only minimal energy input to transition from solid to vapor. Carbon monoxide, with its sublimation temperature of just 28 Kelvin at vacuum conditions, begins to vaporize from the warmest surface regions while the bulk of the nucleus remains frozen solid. Molecular nitrogen, even more responsive to temperature changes, starts to exhibit measurable vapor pressure at temperatures that seem impossibly low by terrestrial standards. The scientific mystery embedded in this early outgassing lies in understanding how such volatile compounds survive the comet's 4 billion-year journey through space. Theoretical models suggest that carbon monoxide and molecular nitrogen have been lost to sublimation long ago, even under the extreme cold conditions of the Oort cloud. The persistence of these compounds in measurable quantities suggests preservation mechanisms more effective than previously understood, possibly involving complex chemical interactions within the ice matrix or physical shielding by less volatile materials. As the outgassing begins, it creates the first visible evidence of the comet's return to activity. The released gases expand rapidly in the near-vacuum conditions surrounding the nucleus, forming a tenuous atmosphere called the coma. Initially, this coma remains invisible to most telescopes. The gas densities are far too low to scatter significant amounts of sunlight. Yet sensitive spectrographic instruments begin to detect the characteristic absorption and emission lines that betray the presence of specific molecular species. The composition of the early coma provides astronomers with their first glimpse into the comet's preserved chemistry. Carbon monoxide produces distinctive infrared emissions at wavelengths near 4.6 micrometers, while molecular nitrogen remains largely invisible except through its effects on other spectral features. More surprisingly, the coma shows evidence of organic compounds, complex carbon-based molecules that speak of chemical processes occurring within the warming nucleus. The sublimation process creates pressure differentials within the comet's porous structure that drive gas flow toward the surface. As volatile compounds vaporize in subsurface regions, they must migrate through the interconnected network of pores and cavities that characterizes the nucleus interior. This migration process carries with it tiny particles of dust and ice, beginning the formation of the visible dust coma that will eventually make the comet detectable to ground-based observers. The dust component of the early outgassing provides additional clues about the comet's formation and preservation history. Spectroscopic analysis reveals mineral compositions consistent with formation in the cold outer regions of the solar nebula, including high abundances of water ice and evidence for organic compounds that form through low-temperature chemistry. The dust-to-gas ratio, a fundamental parameter that describes the relative amounts of solid and gaseous material released, differs significantly from values typical of short-period comets, suggesting that 3I Atlas has retained more of its original volatile inventory. The thermal evolution of the nucleus proceeds with increasing complexity as solar heating penetrates deeper into the interior. Heat conduction through the porous ice and dust matrix creates a wave of warming that propagates inward at rates determined by the thermal properties of the constituent materials. The process resembles the seasonal thawing of permafrost, but operating under conditions of temperature and pressure far removed from terrestrial experience. Within the warming layers, chemical processes begin to stir for the first time in geological ages. Organic molecules that have remained essentially frozen since the comet's formation start to exhibit mobility and reactivity. Radiolysis products, the chemical fragments created by cosmic ray bombardment over millions of years, begin to recombine into more complex structures. The result is a chemistry laboratory operating at temperatures and pressures that cannot be duplicated in earthly experiments. The isotopic signatures preserved within the released gases begin to tell their story to astronomers equipped with sensitive spectrographic instruments. The ratio of deuterium to hydrogen in water vapor, for example, carries information about the temperature and pressure conditions under which the original ice condensed from the solar nebula. Carbon isotope ratios in the released carbon monoxide reflect the nuclear processes that occurred within previous generations of stars, providing a direct link to the galactic chemical evolution that preceded the solar system's formation. The scientific puzzle deepens as observations reveal isotopic compositions that differ significantly from those of other comet populations. The deuterium enrichment in the water vapor exceeds that of most short-period comets, suggesting formation under different thermal conditions or in a different region of the early solar system. The carbon isotope ratios show variations that hint at multiple sources of organic carbon, possibly reflecting both interstellar inheritance and solar nebula processing. As the comet continues its slow approach toward the inner solar system, the outgassing rate gradually increases in response to rising temperatures and more intense solar radiation. Yet the activity remains sporadic and localized, controlled by the complex interplay of solar heating, thermal inertia, and the comet's irregular rotation. Some regions of the surface begin to show visible changes as sublimation removes surface materials and exposes fresh ice beneath, while other areas remain apparently dormant. The coma begins to expand and brighten as more gas and dust join the growing envelope around the nucleus. What started as an invisible cloud of trace gases gradually becomes substantial enough to scatter sunlight, creating the diffuse glow that characterizes active comets. The process unfolds with geological patience. Changes that occur over days or weeks for comets in the inner solar system require months or years for a body still beyond the orbit of Uranus. The awakening of 3I Atlas represents more than just a physical transformation. It marks the beginning of the comet's role as a scientific messenger carrying information from the solar system's birth. Each molecule of gas released from the warming nucleus, each grain of dust liberated by sublimation, carries within its chemical structure a record of conditions that existed when the solar system was young. The comet's return to activity after millions of years of dormancy provides astronomers with an unprecedented opportunity to study pristine materials from the era of planetary formation. The irony of the situation becomes more apparent as the awakening progresses. The very process that makes the comet observable and scientifically accessible, the sublimation of its volatile inventory, simultaneously begins to destroy the pristine record it has preserved for billions of years. Each day of activity represents a tiny loss of the finite volatile budget that the comet accumulated during its formation, a gradual erosion of the chemical library that makes it so valuable to planetary science. As 3I Atlas continues its journey toward the inner solar system, carrying within its slowly awakening heart the molecular memory of the solar system's youth, it faces the fundamental paradox that governs all scientific observation. To be studied, it must become active. To become active, it must sacrifice portions of the very materials that make it worth studying. In this cosmic trade-off between preservation and accessibility, the comet begins to write its own obituary even as it tells the story of its ancient birth. The transformation from dormant ice ball to active comet accelerates as 3I Atlas crosses the orbit of Saturn, entering a region of space where solar radiation becomes intense enough to drive substantial outgassing from materials that have remained frozen for millions of years. At this distance, roughly 10 astronomical units from the Sun, the surface temperature of the nucleus reaches temperatures above 100 Kelvin, crossing critical thresholds for the sublimation of various volatile compounds. What begins as a gentle stirring of surface materials rapidly evolves into a complex dance of gas and dust that challenges existing models of comet behavior. The most striking aspect of the comet's awakening lies not in the familiar sublimation of water ice, but in the unexpected abundance of more volatile compounds that continue to stream from the nucleus long after they should have been depleted. Carbon monoxide outgassing, which typically dominates comet activity only at large distances from the Sun, persists at rates that suggest vast reservoirs preserved within the interior. The phenomenon puzzles astronomers who have studied dozens of other long-period comets, none of which have displayed such persistent hypervolatile activity. The physics underlying this unusual behavior begins to reveal itself through careful spectroscopic analysis of the expanding coma, instead of the simple sublimation of surface ices that characterizes most comet outgassing. 3R Atlas appears to be releasing materials from deeper within its interior, possibly through a process astronomers term crystallization-driven outgassing. The amorphous water ice that formed under the rapid cooling conditions of the early solar system begins to transform into crystalline phases as temperatures rise, releasing trapped gases that have been locked within the ice matrix for billions of years. The process operates like a cosmic pressure cooker operating in reverse. As the amorphous ice undergoes structural transformation, it releases not only the gases directly trapped within its molecular structure, but also larger volatile molecules that were incorporated during the comet's original formation. The result is outgassing that include not just simple compounds like water vapor and carbon monoxide, but complex organic molecules that speak of chemical processes occurring in the warming interior. Molecular nitrogen, that most volatile of common compounds, streams away from the nucleus in quantities that defy theoretical expectations. Computer models of comet evolution suggest that such volatile compounds should be depleted from the surfaces of long-period comets within a few thousand years of their formation, lost to space during the object's original journey outward from the inner solar system. Yet 3R Atlas continues to release molecular nitrogen at rates comparable to its carbon monoxide production, suggesting preservation mechanisms more effective than previously understood. The scientific mystery deepens when astronomers analyze the isotopic composition of the released gases. The carbon monoxide shows isotopic ratios that differ significantly from those of the interstellar medium, indicating processing within the solar nebula before incorporation into the comet nucleus. Yet the ratios also differ from those typical of inner solar system materials, suggesting formation in a region of the protoplanetary disk with unique chemical characteristics. The molecular nitrogen presents an even greater puzzle. Its isotopic signature closely matches that of Earth's atmosphere, implying formation under temperature and pressure conditions similar to those that produce the volatile inventory of the inner planets. This similarity challenges models of solar system formation that place the comet's origin in the cold outer regions of the protoplanetary disk, where nitrogen isotope ratios should differ significantly from terrestrial values. As the outgassing intensifies, the coma begins to develop structure that reflects the complex topography and thermal properties of the nucleus surface. Jets of gas and dust emerge from specific regions, creating fan-shaped plumes that extend thousands of kilometers into space. These jets appear to originate from areas where subsurface ice has been exposed by the removal of overlying dust layers, creating localized regions of enhanced activity. The dust component of the coma provides additional surprises for studying astronomers. Instead of the simple mixture of silicate grains and organic compounds typical of most comets, 3I Atlas releases particles that include significant amounts of crystalline ice, tiny fragments of the nucleus interior that have been liberated by gas pressure and ejected into space. These ice particles sublimate rapidly in the vacuum surrounding the nucleus, but not before providing brief glimpses of the comet's internal structure and composition. Spectroscopic analysis of the dust reveals mineral compositions consistent with formation in the outer solar system, including abundant water ice and evidence for organic compounds formed through low-temperature chemistry. Yet the dust also contains unexpected components, including refractory grains that appear to have formed at high temperatures near the early sun, before being transported to the cold outer regions where the comet accreted. The presence of these high-temperature minerals in a body that formed in the cold outer solar system speaks to the dynamic nature of the early protoplanetary disk. Turbulent mixing processes must have transported materials across vast distances, creating comet nuclei with compositions that reflect both local formation conditions and the global chemical evolution of the solar nebula. 3I Atlas becomes not just a sample of outer solar system materials, but a repository of components from throughout the early solar system. The outgassing process creates feedback effects that influence the comet's thermal evolution in unexpected ways. As gases expand away from the nucleus, they carry with them thermal energy that would otherwise be available to heat subsurface materials. This cooling effect, known as sublimation refrigeration, helps to stabilize the interior temperature and prevent the complete loss of volatile compounds during the comet's approach to the Sun. Simultaneously, the removal of surface materials by sublimation exposes deeper layers to solar heating, creating a self-sustaining process that gradually excavates the nucleus interior. The phenomenon resembles the retreat of a glacier, but operating through sublimation rather than melting, and occurring under vacuum conditions that have no terrestrial analogue. The complex interplay between heating, sublimation, and gas flow creates patterns of activity that vary with the comet's rotation and orbital position. As different regions of the surface rotate into sunlight, they experience thermal cycles that drive episodic outgassing events. The result is a comet whose brightness and activity level fluctuate in ways that reflect the detailed topography and composition of its surface. The scientific challenge lies in interpreting these observations to understand the comet's formation history and interior structure. Each spectral line, each variation in brightness, each change in gas composition carries information about conditions that existed during the solar system's youth. Yet extracting this information requires sophisticated theoretical models that can account for the complex physics of sublimation, gas flow, and radiative transfer under extreme conditions. The coma continues to expand and evolve as the comet approaches the orbit of Jupiter, developing the classic teardrop shape that results from solar radiation pressure acting on the dust and gas. The anti-tail direction, pointing away from the Sun, becomes more pronounced as the solar wind begins to interact with the ionized components of the coma, creating the beginnings of the plasma tail that will eventually extend millions of kilometers behind the nucleus. Yet throughout this dramatic transformation from dormant ice ball to active comet, the most remarkable aspect of 3I Atlas remains its persistent release of hypervolatile compounds that should have been lost long ago. Each day brings new evidence that this ancient wanderer has preserved a chemical inventory unlike any other comet in the astronomical record, a molecular library that offers unprecedented insights into the conditions that existed during the solar system's formation. The irony of the comet situation becomes more poignant as its activity increases. The very processes that make it scientifically valuable, the release of preserved gases and the exposure of interior materials, simultaneously destroy the pristine record that took billions of years to preserve. Each molecule that escapes to space represents a tiny loss of the finite chemical inventory that makes 3I Atlas such an extraordinary messenger from the cosmic past. As the comet continues its approach toward the inner solar system, it faces the fundamental challenge that confronts all scientific specimens from the deep past. To reveal their secrets, they must be altered or destroyed in the process of observation. The comet's gift to human knowledge comes at the cost of its own pristine preservation, a cosmic sacrifice that transforms billions of years of patient waiting into brief moments of scientific revelation. The spectroscopic revelation begins at wavelengths invisible to human eyes, in the infrared portion of the electromagnetic spectrum where molecules announce their presence through characteristic patterns of absorption and emission. As 3I Atlas crosses the orbit of Jupiter, entering the realm where ground-based telescopes can capture sufficient photons for detailed analysis, astronomers begin to decipher the chemical vocabulary written in starlight filtered through the comet's expanding coma. Each spectral line tells a story of molecular bonds formed billions of years ago, preserved in the frozen archive of the nucleus, and now liberated to shine briefly in the vacuum of space before dispersing forever into the cosmic background. The carbon monoxide signature emerges first in the observations, its fundamental vibrational transition at 4.67 micrometers appearing with an intensity that immediately catches the attention of comet researchers. The strength of this emission line suggests carbon monoxide abundances far exceeding those of typical long-period comets, which typically show only trace amounts of this hypervolatile compound by the time they reach Jupiter's orbital distance. Yet 3I Atlas continues to release carbon monoxide at rates that imply vast reservoirs remain locked within its interior, challenging models of volatile depletion that have successfully explained the behavior of other comet populations. The isotopic analysis of the carbon monoxide provides even more intriguing puzzles for researchers attempting to reconstruct the comet's formation history. The ratio of carbon-13 to carbon-12 isotopes differs significantly from the values measured in the interstellar medium, indicating that the carbon monoxide underwent chemical processing within the solar nebula before incorporation into the comet nucleus. Yet the isotopic signature also differs from measurements of carbon monoxide in the atmospheres of the giant planets, suggesting that the comet formed in a region of the protoplanetary disk with unique chemical characteristics. The oxygen isotopes tell a complementary story of complex formation processes and multiple sources of raw materials. The ratio of oxygen-18 to oxygen-16 in the carbon monoxide molecule carries information about the nuclear reactions that created these isotopes within previous generations of stars, the stellar nucleosynthesis that seeded the molecular cloud from which the solar system eventually formed. The measured ratios suggest contributions from both massive stars that ended their lives in supernova explosions and intermediate mass stars that expelled their outer layers through stellar winds. Molecular nitrogen presents the most challenging spectroscopic target, as this symmetric molecule produces no infrared emissions under typical comet conditions. Its presence must be inferred through more subtle signatures, such as its effect on the rotational and vibrational states of other molecules, or through rare electronic transitions that occur only under specific conditions of temperature and radiation field strength. Yet careful analysis of high-resolution spectra reveals evidence for molecular nitrogen abundances that exceed theoretical expectations by factors of 10 or more. The scientific mystery embedded in these observations lies in understanding how molecular nitrogen, the most volatile of common compounds, could survive in measurable quantities within a comet that has existed for billions of years. Theoretical calculations suggest that molecular nitrogen should sublimate completely from comet surfaces at temperatures above 30 Kelvin, escaping to space during the object's original journey from the inner solar system to the Oort cloud. The persistence of significant nitrogen reservoirs within 3I Atlas implies preservation mechanisms that operate with extraordinary efficiency, possibly involving chemical incorporation into clathrate structures or physical isolation within the deepest regions of the nucleus. The water vapor spectrum, while more familiar to comet astronomers, reveals its own collection of anomalies and unexpected features. The deuterium to hydrogen ratio in the released water vapor exceeds that of Earth's oceans by a factor of 3, placing it among the most deuterium-enriched water measured in solar system objects. This isotopic signature carries information about the temperature conditions under which the water originally condensed from the solar nebula, with higher deuterium ratios indicating formation at lower temperatures in more distant regions of the protoplanetary disk. Yet the water spectrum also shows evidence for multiple isotopic components, suggesting that the comet contains water formed under different conditions or derived from different sources. Some spectral features match the isotopic composition of water in carbonaceous meteorites, implying a connection to the asteroid belt region of the early solar system. Other components show isotopic ratios more similar to interstellar ice, suggesting that some of the comet's water inventory predates the solar system's formation and was inherited directly from the molecular cloud that gave birth to the Sun and planets. The organic chemistry revealed through spectroscopic analysis provides perhaps the most tantalizing glimpses into the complex chemical processes that occurred within the early solar system. Methanol, formaldehyde, and hydrogen cyanide appear in the coma spectrum with abundances that speak of active organic synthesis occurring within the warming nucleus. These simple organic compounds represent the building blocks of more complex chemistry, the molecular precursors that could eventually lead to the amino acids, nucleotides, and other compounds essential for life. More complex organic molecules remain tantalizingly beyond the detection limits of current spectroscopic techniques, their presence inferred through indirect signatures and the identification of their simpler fragmentation products. The warming interior of the comet nucleus may contain a chemical library of organic compounds synthesized through 4 billion years of slow radiolysis and intermolecular reactions, a collection of molecules that represents one of the longest-running chemistry experiments in the solar system. The temporal evolution of the spectroscopic signatures provides additional clues about the physical structure and thermal properties of the nucleus interior. As the comet continues its approach toward the Sun, the relative abundances of different molecular species change in ways that reflect the progressive heating of deeper layers within the nucleus. Carbon monoxide production peaks early in the approach sequence, then gradually declines as surface reservoirs become depleted. Water vapor production follows a different pattern, increasing steadily as solar heating penetrates to the water-rich interior layers. The phenomenon of crystallization-driven outgassing becomes apparent through careful monitoring of the temporal changes in gas production rates and composition. As the amorphous water ice that comprises much of the nucleus interior undergoes structural transformation to crystalline phases, it releases not only trapped gases, but also the latent heat of crystallization. This thermal energy drives additional sublimation and creates feedback effects that can sustain outgassing rates even as surface temperatures begin to stabilize. The dust component of the coma provides complementary information about the nucleus composition through its own spectroscopic signatures. Silicate minerals reveal themselves through characteristic absorption features in the infrared spectrum, indicating compositions consistent with formation in the outer regions of the solar system. Yet the dust also contains components that appear to have formed at high temperatures, including crystalline olivine and pyroxene grains that require formation temperatures exceeding 1000 Kelvin. The presence of high-temperature minerals in a comet that formed in the cold outer solar system provides strong evidence for radial mixing processes within the early protoplanetary disk. Turbulent transport mechanisms must have carried materials formed near the young sun outward to the regions where comets accreted, creating nuclei with compositions that reflect the global chemical evolution of the solar nebula rather than purely local formation conditions. The isotopic signatures of the dust minerals provide additional constraints on these mixing processes and the thermal history of the early solar system. Oxygen isotope ratios in the crystalline silicates show variations that reflect different formation environments and processing histories, some matching the compositions of meteorites from the asteroid belt, while others appear more exotic and difficult to place within current models of solar system formation. The scientific challenge lies in synthesizing these diverse spectroscopic observations into a coherent model of the comet's formation, preservation, and current activity. Each molecular species tells part of the story, but the complete narrative requires understanding the complex interplay between chemistry and physics and dynamics that operated during the solar system's youth. The comet becomes a Rosetta Stone for deciphering the conditions that existed during planetary formation, its chemical composition encoding information about process that occurred before Earth existed in recognizable form. The observational campaign intensifies as the comet approaches the orbit of Mars, with telescopes around the world and in space dedicating observing time to capturing the fleeting spectroscopic signatures of this ancient messenger. Each spectrum represents a brief snapshot of chemical processes that have been frozen in time for billions of years, now briefly illuminated by solar radiation before the molecules disperse forever into the cosmic background. The irony inherent in these observations becomes more apparent with each passing day. The very act of spectroscopic analysis requires the comet to destroy portions of the pristine record it has preserved for so long. Each molecule that absorbs and re-emits photons in characteristic spectral lines represents a tiny piece of evidence about the solar system's formation, yet that same molecule is simultaneously being lost to space, never to return to the nucleus that preserved it through deep cosmic time. As the spectroscopic signatures continue to evolve and intensify, they provide a real-time record of the comet's transformation from ancient ice ball to active messenger. The chemistry written in starlight tells a story that spans from the birth of stars in distant molecular clouds, through the collapse of the solar nebula and the formation of the planets, to the present moment when human technology has advanced sufficiently to read the molecular messages preserved within this wandering archive of cosmic history. The comet's gift to human knowledge unfolds photon by photon, spectrum by spectrum, as astronomers around the world work to decode the chemical vocabulary that speaks of times when the solar system was young and Earth was nothing more than an accumulating mass of cosmic debris orbiting a star that had not yet learned to nurture life. The carbon monoxide rebellion against theoretical expectations manifests most clearly in production rate measurements that confound every model of comet evolution developed over the past century of astronomical observation. As 3I Atlas approaches the orbit of Mars, still receiving only a fraction of the solar radiation that reaches Earth, it continues to release carbon monoxide at rates that would be impressive for a comet at half the distance from the Sun. The phenomenon challenges fundamental assumptions about volatile distribution and preservation within comet nuclei, forcing astronomers to reconsider mechanisms that could maintain hypervolatile reservoirs over geological timescales. The molecular structure of carbon monoxide itself provides clues to understanding this unexpected behavior. With its triple bond between carbon and oxygen atoms, carbon monoxide represents one of the strongest chemical bonds found in simple molecules, yet paradoxically remains one of the most volatile compounds under astronomical conditions. The binding energy that holds the molecule together exceeds that of most other small molecules, making it stable against photodissociation and chemical reaction, yet its weak intermolecular forces allow it to sublime directly from solid to gas at temperatures barely above absolute zero. This combination of molecular stability and physical volatility creates ideal conditions for long-term preservation within comet nuclei. Provided the right physical and chemical environment exists to prevent escape. The carbon monoxide now streaming from 3I Atlas appears to originate from reservoirs that have remained isolated from the surface for billions of years, protected by layers of less volatile materials, trapped within crystalline matrices that have only recently begun to destabilize under solar heating. The distribution of carbon monoxide within the nucleus reveals itself through the temporal pattern of its release. Instead of the gradual decline in production rate that characterizes the depletion of surface volatile reservoirs, the carbon monoxide flux shows complex variations that suggest multiple sources operating at different depths within the interior. Some production appears linked to direct sublimation from near-surface regions, while other components seem to originate from deeper layers where structural changes in the ice matrix liberate previously trapped gases. The isotopic composition of the released carbon monoxide provides the most compelling evidence for its ancient preservation and primordial origin. The ratio of carbon-13 to carbon-12 isotopes shows values intermediate between those of the interstellar medium and the inner solar system, suggesting formation within the solar nebula under conditions that allowed some isotopic fractionation but preserved signatures of the original molecular cloud chemistry. The oxygen isotope ratios tell a similar story, with values that reflect nuclear processes within previous stellar generations, but show evidence for modification during solar nebula evolution. More intriguingly, the isotopic ratios vary with time as the comet's activity evolves, suggesting that different carbon monoxide reservoirs within the nucleus have slightly different formation histories or preservation environments. Early in the outgassing sequence, the isotopic signatures more closely match interstellar values, as if the first released carbon monoxide represents the most pristine material. Later releases show progressive shifts toward values more typical of inner solar system objects, possibly reflecting contamination with carbon monoxide formed through different pathways or under different conditions. The spatial distribution of carbon monoxide emission from the nucleus provides additional insights into the physical processes controlling its release. Observations with high spatial resolution show that carbon monoxide jets originate from specific regions of the surface, often coinciding with areas where thermal infrared observations indicate temperatures slightly above average. These localized emission sources suggest that carbon monoxide release depends critically on thermal activation processes that require specific threshold temperatures or thermal cycling to operate effectively. The relationship between carbon monoxide production and water vapor release reveals the complex interplay between different volatile species within the warming nucleus. Unlike water vapor, which shows production rates that correlate strongly with solar heating and surface temperature, carbon monoxide production appears more episodic and less directly tied to insolation patterns. This behavior suggests that carbon monoxide release depends on structural changes within the ice matrix, rather than simple thermal sublimation from surface layers. Laboratory experiments on carbon monoxide clathrates, crystalline structures where carbon monoxide molecules become trapped within cages of water ice, provide potential explanations for the comet's unusual behavior. These studies show that carbon monoxide can remain stable within clathrate structures at temperatures well above its normal sublimation point, but releases rapidly when the clathrate structure becomes destabilized by heating or crystallization processes. The comet's interior may contain vast reservoirs of such clathrate materials formed during the original accretion process and preserved through billions of years of frozen storage. The quantum mechanical properties of carbon monoxide molecules add another layer of complexity to understanding their preservation and release. At the extremely low temperatures characteristic of the Oort cloud environment, quantum effects begin to influence molecular behavior in ways that have no classical analogue. Quantum tunneling may allow carbon monoxide molecules to migrate through crystalline barriers that would be impermeable under classical physics. While quantum mechanical selection rules affect the efficiency of various chemical and physical processes, the scientific puzzle deepens when astronomers compare the carbon monoxide behavior of 3I Atlas with that of other long-period comets that have returned from the Oort cloud. Most such objects show little or no carbon monoxide emission by the time they reach the orbit of Mars, having apparently exhausted their hypervolatile inventories during earlier stages of their approach. The persistence of strong carbon monoxide emission from 3I Atlas suggests either exceptional preservation conditions during its formation or unusual structural properties that protect volatile reservoirs more effectively than in typical comet nuclei. The implications extend beyond the specific case of 3I Atlas to broader questions about volatile preservation in small solar system bodies. If carbon monoxide can survive for billions of years within comet nuclei under the right conditions, similar preservation mechanisms might operate for other hypervolatile compounds, creating chemical libraries that preserve records of the early solar system's composition and evolution. The comet becomes not just an individual scientific specimen, but a proof-of-concept demonstration that pristine materials from the solar system's formation can survive the journey through deep cosmic time. The production rate measurements continue to surprise observers as the comet maintains carbon monoxide emission rates that exceed those of water vapor, a reversal of the typical pattern seen in most active comets. This unusual composition signature suggests that 3I Atlas preserves a volatile inventory more representative of outer solar system formation conditions, where carbon monoxide condensation could occur alongside water ice formation in the cold outer regions of the protoplanetary disk. The temporal stability of the carbon monoxide emission provides clues about the physical processes controlling its release from the nucleus interior. Unlike many volatile species that show strong diurnal variations linked to the comet's rotation and solar heating patterns, carbon monoxide production remains relatively constant over timescales of days to weeks. This stability suggests that the emission originates from thermal processes operating deep within the nucleus, where temperature variations occur over much longer timescales than surface heating cycles. The mystery of carbon monoxide persistence in 3I Atlas represents more than just an interesting astronomical observation. It challenges fundamental assumptions about volatile evolution in the outer solar system and raises questions about the chemical inventory available for planetary formation processes. If hypervolatile compounds could be preserved within solid bodies over billion-year timescales, they might have played more important roles in the chemical evolution of planetary atmospheres and the development of conditions suitable for life than previously recognized. As the comet continues its approach toward the inner solar system, its rebellious carbon monoxide continues to stream away, carrying with each departing molecule a piece of evidence about conditions that existed when the solar system was young. The ongoing emission represents both a scientific opportunity and a countdown timer. Each day brings new observations and insights, but also marks the irreversible loss of materials that took billions of years to preserve and can never be replaced once they escape to the vacuum of space. Molecular nitrogen whispers its presence through the most subtle of signatures, invisible to direct observation, yet detectable through its profound influence on the behavior of other species within the expanding coma. This diatomic molecule, composed of two nitrogen atoms bound by one of the strongest triple bonds in chemistry, represents perhaps the most elusive component of the comet's volatile inventory, requiring sophisticated analytical techniques to confirm its presence and measure its abundance. Yet the evidence for substantial nitrogen reservoirs within 3I Atlas grows stronger with each passing day, challenging every theoretical model of volatile preservation in comets and raising fundamental questions about the chemical conditions that existed during the solar system's formation. The indirect detection of molecular nitrogen relies on its interaction with other coma constituents, particularly its ability to collisionally excite carbon monoxide molecules into higher rotational states that produce observable infrared emissions. As nitrogen molecules expand away from the nucleus, they collide with carbon monoxide molecules at velocities determined by the temperature and pressure conditions near the surface. These collisions transfer rotational energy to the carbon monoxide molecules, populating higher energy states that decay by emitting photons at characteristic wavelengths. The intensity and population distribution of these collision-induced emissions provide a measure of the nitrogen density within the inner coma, allowing astronomers to estimate the molecular nitrogen production rate despite the lack of direct spectroscopic signatures. The calculations require sophisticated models of gas dynamics and molecular collision processes, accounting for the complex three-dimensional structure of gas flow away from the irregularly shaped nucleus and the temperature variations that affect collision cross-sections and energy transfer efficiency. The estimated nitrogen production rates exceed theoretical expectations by factors that challenge fundamental assumptions about comet composition and evolution. Computer models of volatile loss during a comet's journey from the inner solar system to the Oort cloud predict that molecular nitrogen should be completely depleted from nucleus surfaces within a few thousand years, lost to space during the initial warming phase of the outward journey. The persistence of measurable nitrogen emission from 3I Atlas implies preservation mechanisms of extraordinary efficiency, possibly involving trapping within clathrote structures or physical sequestration in the deepest regions of the nucleus interior. The isotopic composition of the molecular nitrogen provides the most compelling evidence for its ancient origin and pristine preservation. The ratio of nitrogen-15 to nitrogen-14 isotopes, measured through the subtle effects of isotopic substitution on collision-induced emission intensities, shows values that closely match those of Earth's atmospheres. This similarity proves remarkable given the vast differences in formation environment and subsequent evolution between the comet's nitrogen and terrestrial atmospheric nitrogen, suggesting either common source materials or convergent isotopic evolution through processes that remain poorly understood. The terrestrial connection raises intriguing questions about the role of comets in delivering volatile compounds to the inner planets during the early phases of solar system evolution. If comets like 3I Atlas preserve nitrogen with isotopic compositions similar to Earth's atmosphere, they represent potential source reservoirs for the volatile inventories that eventually gave rise to planetary atmospheres and, ultimately, the chemical conditions necessary for life. The comet becomes not just a messenger from the past, but a potential ancestor of the air that surrounds our planet. The physical chemistry of nitrogen preservation within ice matrices operates through mechanisms that push the boundaries of current understanding. Molecular nitrogen, with its symmetrical structure and lack of permanent electric dipole moment, interacts only weakly with other molecules through van der Waals forces. Yet under the extreme pressure and temperature conditions that may exist within comet interiors, even these weak interactions can lead to the formation of stable inclusion complexes and clathrate structures that effectively trap nitrogen molecules within crystalline cages. Laboratory experiments attempting to reproduce these preservation conditions face fundamental challenges in recreating the unique environment of comet formation and evolution. The pressures generated by gravitational compaction within comet nuclei remain small by terrestrial standards, yet the combination of low temperature, long time scales, and complex chemical environments creates conditions that cannot be duplicated in earthly laboratories. The comet nucleus becomes its own 4 billion-year experiment in high-pressure, low-temperature chemistry, with results that challenge and extend theoretical understanding. The temporal evolution of nitrogen emission as the comet approaches the Sun provides clues about the depth distribution and thermal properties of nitrogen-rich regions within the nucleus. Unlike carbon monoxide, which shows evidence for multiple source regions at different depths, nitrogen emission appears to originate primarily from relatively shallow subsurface layers that respond quickly to changes in solar heating. This distribution suggests that nitrogen preservation may require specific temperature and pressure conditions that exist only within narrow depth ranges of the nucleus interior. The quantum mechanical properties of molecular nitrogen add additional complexity to understanding its preservation and release mechanisms. At the extremely low temperatures characteristic of comet interiors, quantum effects influence the rotational and vibrational states of nitrogen molecules in ways that affect their chemical reactivity and physical properties. Quantum tunneling processes may allow nitrogen molecules to migrate through crystalline barriers more readily than classical physics would predict, while quantum mechanical selection rules influence the efficiency of energy transfer processes that control sublimation rates. The relationship between nitrogen emission and the comet's rotational state reveals information about the spatial distribution of nitrogen sources across the nucleus surface. Observations show that nitrogen production rates vary with rotational phase, but with patterns that differ from those of other volatile species. This behavior suggests that nitrogen-rich regions may be preferentially located in areas with specific thermal or structural properties, possibly reflecting heterogeneities in the original accretion process or subsequent evolution of the nucleus interior. The detection of molecular nitrogen in 3I Atlas represents more than just the identification of another volatile species. It provides direct evidence that the most chemically inert components of the solar nebula could be preserved within solid bodies over geological timescales. Nitrogen's chemical unreactivity makes it an ideal tracer of physical processes, as its abundance and isotopic composition reflect primarily the conditions of formation and preservation rather than subsequent chemical modification. The implications extend to understanding the volatile inventories available during the early phases of planetary formation. If substantial amounts of molecular nitrogen could be preserved within the solid bodies that eventually accreted to form planets, this hypervolatile compound may have played more important roles in early planetary evolution than previously recognized. The late heavy bombardment that scarred the inner planets during the first billion years of solar system history may have delivered not just water and organic compounds, but also significant amounts of molecular nitrogen that contributed to early atmospheric development. The mystery of nitrogen preservation within 3I Atlas deepens when compared to observations of other comet populations. Short-period comets, which have undergone multiple passages through the inner solar system, show no evidence for molecular nitrogen emission, having apparently lost their entire inventory of this hypervolatile compound during thermal processing. Even most long-period comets show little or no nitrogen emission, suggesting that the preservation conditions achieved by 3I Atlas represent something exceptional rather than typical of Oort cloud objects. The ongoing nitrogen emission from the comet provides a natural laboratory for studying the physical chemistry of this important but elusive molecule under conditions that cannot be reproduced on Earth. Each departing nitrogen molecule carries information about the temperature, pressure, and chemical environment of its formation and storage within the nucleus, offering insights into processes that operated during the solar system's youth. Yet each departed molecule also represents an irreversible loss of material that took billions of years to preserve and cannot be replaced. As 3I Atlas continues its approach toward the inner solar system, its quiet nitrogen emission continues to whisper secrets of the early solar nebula, speaking in a chemical language that requires the most sophisticated instruments and theoretical models to decipher. The nitrogen molecules streaming away from the ancient nucleus carry within their quantum mechanical structure the memory of an epoch when the solar system was young and the future of planetary evolution remained unwritten. The persistence of outgassing activity as 3I Atlas begins its journey away from the Sun confounds every theoretical model developed to predict comet behavior, creating a scientific puzzle that challenges fundamental assumptions about volatile distribution and thermal evolution in these ancient ice bodies. Most comets display predictable patterns of activity that peak near perihelion, decline rapidly as they recede from the Sun's warming influence. Following well-understood relationships between solar heating, surface temperature, and sublimation rates, yet 3I Atlas defies these expectations, maintaining robust gas and dust production at distances where other comets have long since returned to dormancy. The phenomenon becomes apparent through careful monitoring of the comet's brightness and spectroscopic signatures as it passes through the orbit of Mars on its outbound trajectory. Instead of the expected exponential decline in activity that should accompany decreasing solar heating, the comet continues to exhibit strong carbon monoxide emission and substantial dust production, water vapor emission, while somewhat reduced compared to perihelion levels, remains detectable at distances where theoretical models predict complete cessation of sublimation from surface ice reservoirs. The thermal physics underlying this unusual behavior appears to involve processes operating deep within the nucleus interior, where temperature changes occur over much longer timescales than surface heating cycles. As the comet approached the Sun, solar radiation penetrated progressively deeper into the porous nucleus structure, depositing thermal energy in subsurface regions through the slow process of radiative diffusion. This stored thermal energy now drives continued outgassing as the comet recedes, creating a thermal lag effect that extends activity far beyond the period of direct solar heating. Computer simulations of nucleus thermal evolution suggest that the effect should diminish over time scales of months to years, as the stored thermal energy radiates away to space and interior temperatures return to equilibrium values. Yet observations of 3I Atlas show persistent activity extending far beyond these theoretical timescales, indicating either exceptional thermal properties of the nucleus material or additional energy sources not accounted for in standard models of comet thermal evolution. The continued release of hypervolatile compounds presents the greatest challenge to theoretical understanding. Carbon monoxide and molecular nitrogen, with their extremely low sublimation temperatures, should respond almost instantaneously to changes in solar heating, showing activity patterns that closely track the comet's distance from the Sun. The persistence of strong hypervolatile emission at large solar distances suggests that these compounds continue to be released from interior reservoirs through processes unrelated to direct solar heating. One possibility involves the crystallization of amorphous water ice within the nucleus interior, a process that releases latent heat of crystallization and can drive continued sublimation of nearby volatile compounds. As temperatures throughout the nucleus slowly equilibrate following perihelion passage, regions of amorphous ice that remained below the crystallization threshold during the approach phase may undergo structural transformation during the recession, releasing both thermal energy and trapped gases that have been locked within the ice matrix for billions of years. The spatial distribution of outgassing activity reveals additional clues about the physical processes sustaining continued emission. High-resolution imaging shows that active regions on the nucleus surface remain remarkably stable during the recession phase, with jets and dust emission continuing to originate from the same locations that were active during the approach. This persistence suggests that the outgassing sources are controlled by structural features or compositional heterogeneities within the nucleus, rather than simple thermal response to solar heating. Spectroscopic observations reveal temporal changes in the composition of emitted gases that provide insights into the depth distribution of different volatile species. Early in the recession phase, hypervolatile compounds continue to dominate the emission spectrum, suggesting rapid depletion of near-surface reservoirs and progressive access to deeper interior regions. As the recession continues, the relative abundance of less volatile compounds increases, indicating that the active regions are excavating progressively deeper into the nucleus interior. The dust component of the continued outgassing shows compositional changes that reflect this excavation process. Particles released during the approach phase showed compositions dominated by surface materials that had undergone space weathering and cosmic ray processing over millions of years. Dust emitted during the recession phase shows evidence for less processed materials, including higher abundances of organic compounds and crystalline ice fragments that appear to originate from pristine interior regions. The isotopic signatures of emitted gases continue to evolve during the recession phase, providing a temporal record of the chemical stratification within the nucleus. Early emissions show isotopic compositions characteristic of surface and near-surface materials, while later releases reveal signatures that more closely match primordial values expected for materials preserved since the solar system's formation. This isotopic evolution suggests that the continued outgassing is progressively accessing deeper and more pristine reservoirs of volatile compounds. The scientific mystery deepens when astronomers compare the recession behavior of 3I Atlas with historical observations of other long-period comets. Most such objects show rapid decline to undetectable activity levels within months of perihelion passage, following predictable patterns that match theoretical expectations. The exceptional behavior of 3I Atlas suggests either unusual physical properties of its nucleus or formation conditions that created volatile distributions fundamentally different from those of typical comets. Laboratory studies of ice sublimation under vacuum conditions provide potential explanations for some aspects of the observed behavior. Experiments show that porous ice structures can exhibit complex sublimation patterns that depend on the detailed geometry of pores and channels within the material. As sublimation removes ice from certain regions, it can expose new surfaces and create new pathways for gas flow, sustaining activity through positive feedback processes that continue long after the initial thermal input. The phenomenon of sublimation-driven excavation may play a particularly important role in sustaining the comet's activity during recession. As gas flow removes loosely bound surface materials, It exposes fresh ice surfaces that can continue to sublimate even at reduced temperatures. The process resembles the retreat of terrestrial glaciers, but operating through sublimation rather than melting and occurring under vacuum conditions that create vastly different flow dynamics. The continued emission of organic compounds during the recession phase provides tantalizing evidence for complex chemistry occurring within the warming nucleus interior. Simple organic molecules like formaldehyde and methanol continue to appear in the emission spectrum at levels that suggest active production rather than simple release of stored materials. The chemical processes responsible for this production remain poorly understood, but may involve radiolysis of complex organic precursors or thermal decomposition of larger molecular structures preserved within the nucleus. The implications of sustained outgassing activity extend beyond the specific case of 3I Atlas to broader questions about volatile loss rates and the lifetime of comet nuclei. If comets can maintain substantial activity levels for extended periods following perihelion passage, they may lose larger fractions of their volatile inventories, thus during single orbital passages than previously calculated. This enhanced mass loss could significantly reduce the active lifetimes of comet nuclei and affect estimates of the total population of objects in the Oort cloud. The observational campaign continues as the comet recedes beyond the orbit of Mars, with astronomers racing to capture data while the activity remains detectable. Each spectrum, each photometric measurement, each high-resolution image provides additional pieces of evidence about processes that challenge current understanding of comet physics and chemistry. The comet's refusal to follow theoretical expectations creates both scientific frustration and excitement, forcing researchers to expand their models and consider new mechanisms for volatile preservation and release. The irony of the situation becomes more apparent as observations continue. The very persistence that makes 3A Atlas so scientifically valuable, its continued activity far from the Sun, also accelerates the loss of the pristine materials that make it unique. Each day of extended outgassing represents further depletion of volatile reservoirs that took billions of years to accumulate and preserve. The comet's gift to human knowledge comes at the cost of its own finite chemical inventory, a cosmic trade-off between scientific revelation and material preservation that cannot be reversed or repeated. As 3I Atlas continues its slow journey back toward the outer solar system, carrying within its diminished nucleus the remaining fragments of its molecular library, it faces the fundamental paradox that governs all scientific observation of finite specimens. To reveal their secrets, they must be consumed in the process of revelation. The comet's extended song of outgassing represents both triumph and elegy, a successful delivery of information about the solar system's birth, coupled with the irreversible destruction of the messenger that carried it across billions of years of cosmic time. The escape of hypervolatile compounds from the warming interior of 3I Atlas reveals a hidden architecture of preservation that operated with extraordinary efficiency for billions of years, only to surrender its treasures during the brief thermal awakening of the comet's return to the inner solar system. These exotic ices, compounds so volatile that they remain gaseous under most planetary conditions, had been locked within crystalline matrices and structural cavities that provided protection more effective than any earthly vault, maintaining their molecular integrity across geological timescales that encompass the entire history of complex life on Earth. The physics of hypervolatile sublimation operates according to principles that push the boundaries of current understanding, involving quantum mechanical effects and non-equilibrium thermodynamics that have no terrestrial analogues. Unlike the familiar process of water ice sublimation, which follows well-understood relationships between temperature and vapor pressure, the release of hypervolatile compounds appears to involve cooperative effects where the sublimation of one species triggers cascading release of others, creating complex feedback processes that sustain outgassing rates far beyond simple thermal equilibrium predictions. Methane represents perhaps the most challenging hypervolatile compound to preserve within comet nuclei, as its sublimation temperature of just 91 Kelvin under vacuum conditions makes it vulnerable to loss even under the extreme cold of interstellar space. Yet spectroscopic observations of 3I Atlas reveal methane emission that persists throughout the comet's approach and recession phases, indicating reservoirs that survived 4 billion years of storage in the Oort cloud environment. The preservation mechanism must involve trapping within clathrate hydrate structures, crystalline cages of water molecules that can stabilize methane at temperatures well above its normal sublimation point. The formation of these clathrate structures requires specific pressure and temperature conditions that challenge models of comet nucleus evolution. Laboratory experiments show that methane clathrates remain stable only under pressures exceeding several atmospheres, yet the internal pressure within comet nuclei rarely exceeds a few millibars due to the low gravitational acceleration of these small bodies. The existence of stable methane reservoirs within 3A Atlas implies either unusual formation conditions that created higher internal pressures or clathrate structures with stability properties that differ significantly from those measured in laboratory studies. Carbon dioxide presents a different set of preservation challenges, as this compound can exist as solid ice at temperatures and pressures achievable within comet interiors, yet shows a tendency to segregate from water ice matrices through phase separation processes. The continued release of carbon dioxide from 3I Atlas indicates that substantial reservoirs remained intimately mixed with water ice throughout the comet's history, suggesting formation conditions that favored co-deposition of these compounds or subsequent processes that prevented their separation. The temporal pattern of carbon dioxide release provides clues about the spatial distribution of these reservoirs within the nucleus interior. Unlike hypervolatile compounds that show peak emission during the early phases of outgassing, carbon dioxide production rates increase gradually as the comet approaches the Sun and continue to rise even after perihelion passage. This behavior suggests that carbon dioxide exists primarily in deeper interior regions that require substantial thermal input to reach sublimation temperatures. Ammonia, detected through its characteristic infrared emission lines and photodissociation products in the coma, represents one of the most chemically reactive compounds found in comet nuclei. Its preservation within 3I Atlas for billions of years indicates protection from both thermal decomposition and chemical reaction with other nucleus constituents. The ammonia may exist primarily as hydrates, crystalline compounds where ammonia molecules are incorporated directly into the structure of water ice crystals that provide both chemical protection and thermal stability under extreme conditions. The isotopic composition of the released hypervolatile compounds carries information about their formation environments and subsequent preservation history. Methane shows carbon isotope ratios that differ significantly from those of methane in the atmospheres of the outer planets, indicating formation through different chemical pathways or under different temperature and pressure conditions. The nitrogen isotopes in ammonia closely match those of molecular nitrogen, suggesting common source materials or formation processes. These isotopic signatures provide constraints on theoretical models of volatile distribution within the early solar system, indicating that hypervolatile compounds could condense and be preserved in solid form much closer to the Sun than previously thought possible. The comet's chemical inventory suggests formation in a region of the protoplanetary disk, where temperatures were low enough to allow hypervolatile condensation, yet warm enough to permit the complex chemistry that created the organic compounds also observed in the coma. The sublimation process itself creates additional complexity through the phenomenon of fractionation. where different isotopes of the same element sublime at slightly different rates due to small differences in their vapor pressures. This isotopic fractionation can alter the composition of both the released gases and the remaining solid reservoirs, creating temporal variations in isotopic ratios that provide information about the sublimation process and the structure of volatile reservoirs within the nucleus. The dust component released along with hypervolatile gases shows evidence for intimate physical association between these compounds and the solid matrix of the nucleus. Many dust particles appear to contain inclusions of hypervolatile ices that sublime rapidly after release, creating hollow particle structures that provide insights into the original distribution of volatile compounds within the solid nucleus material. These observations suggest that hypervolatile preservation occurred at the microscopic level, with individual ice crystals and dust grains serving as containers for exotic chemical inventories. The crystallographic analysis of ice particles released from the nucleus reveals structural information about the preservation matrices that protected hypervolatile compounds for billions of years. Many particles show evidence for complex crystal structures that include both water ice and other compounds in ordered arrangements that maximize stability and minimize chemical reactivity. These structures represent natural experiments in solid-state chemistry conducted under conditions of temperature, pressure, and time that cannot be reproduced in terrestrial laboratories. The chemical interactions between different hypervolatile compounds within the nucleus interior appear to influence their preservation and release patterns in ways that remain poorly understood. Some compounds show correlated release patterns that suggest physical association within the nucleus, while others appear to be released independently, indicating spatial separation or different storage mechanisms. These interactions may involve chemical reactions that occur slowly over geological timescales, gradually altering the composition and properties of volatile reservoirs. The thermodynamic properties of hypervolatile compounds under the extreme conditions of comet interiors create additional challenges for theoretical modeling. Standard equations of state that describe the behavior of these compounds under normal laboratory conditions may not apply at the extremely low temperatures and pressures characteristic of comet nuclei. Quantum mechanical effects become important at these conditions, influencing molecular behavior in ways that affect both chemical reactivity and phase stability. The detection of noble gas isotopes in the coma provides additional constraints on hypervolatile preservation mechanisms. These chemically inert compounds can be preserved only through physical trapping within solid matrices, as they form no chemical bonds that could provide stability. The presence of xenon and krypton in the coma indicates that the comet nucleus contains physical structures capable of trapping even these unreactive gases for billions of years. The ongoing release of hypervolatile compounds during the comet's recession phase challenges models that assume simple thermal control of sublimation process. The continued emission of these exotic ices at distances where surface temperatures have dropped well below their sublimation points suggests that release mechanisms involve more than direct thermal activation. Structural instabilities within the nucleus, triggered by thermal cycling during perihelion passage, may create cascading failures in the preservation matrices that sustain hypervolatile release long after the initial thermal input. The spatial distribution of hypervolatile emission sources across the nucleus surface reveals heterogeneities that reflect the original accretion process and subsequent evolution of the comet interior. Some regions show strong emission of all hypervolatile species, suggesting areas where preservation conditions were optimal during the comet's formation. Other regions emit primarily specific compounds, indicating either selective preservation or preferential loss of certain species during the comet's long journey through space. The mass loss rates associated with hypervolatile emission represent a significant fraction of the comet's total volatile budget, despite the small absolute quantities involved. These compounds, preserved through extraordinary effort over geological timescales, disappear into space within months or years of their release. The phenomenon represents one of the most dramatic examples of irreversible loss in the natural world. Materials that required billions of years to accumulate and preserve are consumed in moments of astronomical observation. The scientific value of hypervolatile observations lies not just in their detection, but in the constraints they provide on models of early solar system chemistry and dynamics. The preservation of these exotic compounds within 3I Atlas demonstrates that the outer regions of the protoplanetary disk could maintain chemical conditions suitable for trapping even the most volatile materials, suggesting that the early solar system possessed a more complex and dynamic chemistry than previously recognized. The implications extend to understanding the role of comets in delivering the exotic chemical inventories to planetary surfaces during the early phases of solar system evolution. If hypervolatile compounds could be preserved within comet nuclei and delivered to planetary surfaces through impact processes, they may have contributed rare but chemically important materials that influence the development of planetary atmospheres and surface chemistry. Laboratory attempts to synthesize analogues of the hypervolatile preservation matrices observed in 3I Atlas face fundamental challenges in reproducing the unique conditions of comet formation and evolution. The combination of extremely low temperatures, long-time scales, and cosmic ray irradiation creates chemical environments that push the boundaries of experimental capability. The comet nucleus itself becomes the laboratory, conducting experiments in exotic chemistry that reveal the possibilities and limitations of matter under extreme conditions. The quantum mechanical properties of hypervolatile compounds at extremely low temperatures create additional complexity in understanding their preservation and release. Quantum tunneling effects may allow these molecules to migrate through crystalline barriers in ways that classical physics cannot predict, while quantum mechanical selection rules influence the efficiency of energy transfer processes that control sublimation rates. The comet becomes a natural laboratory for studying quantum effects in complex molecular systems under conditions that cannot be achieved on Earth. The detection of hypervolatile compounds in 3I Atlas represent more than just an expansion of the known chemical inventory of comets. It provides direct evidence that the most exotic components of the solar nebula could be preserved within solid bodies over cosmological timescales. Each departing molecule represents a piece of evidence about chemical processes that operated when the solar system was young, yet each departure also represents an irreversible loss of materials that can never be recovered or replaced. The ongoing sublimation of hypervolatile compounds creates a race against time for astronomical observation. These exotic ices, preserved for 4 billion years in the frozen heart of the comet, will be completely lost within decades of the comet's return to activity. The window for studying these pristine materials from the solar system's formation is measured not in geological time, but in the brief span of human lifetimes, creating urgency for observational campaigns and theoretical analysis. As the hypervolatile compounds continue their exodus from the warming nucleus, they carry within their molecular structures the chemical fingerprints of an epoch when planets were forming and the architecture of the solar system remained fluid and changeable. Their escape represents both scientific triumph and cosmic tragedy, the successful delivery of information about the solar system's chemical birth, coupled with the irreversible destruction of the messenger that preserved it across the vastness of deep time. The comet's surrender of its hypervolatile treasures unfolds with inexorable persistence. each subliming molecule representing a tiny piece of the puzzle that describes how chemical complexity emerged from the simple hydrogen and helium that dominated the early universe. In their brief moment of visibility before dispersing forever into space, these exotic compounds whisper the secrets of cosmic chemistry, speaking a molecular language that took billions of years to preserve and mere moments to lose. Each departing molecule from the warming surface of 3I Atlas carries within its atomic structure a library card to the greatest collection of cosmic information ever assembled, the chemical archive of stellar nucleosynthesis and galactic evolution that spans billions of years before the solar system's birth. The isotopic ratios locked within these simple compounds represent fossil records of nuclear processes that occurred within the hearts of massive stars. The complex web of element formation that transformed the primordial hydrogen and helium of the early universe into the periodic table of elements that makes rocky planets and organic chemistry possible. The carbon atoms streaming away in carbon monoxide molecules bear the nuclear signatures of their stellar birthplaces, their neutron-to-proton ratios reflecting the temperature, pressure, and neutron flux conditions that existed within stellar cores during the final phases of stellar evolution. Carbon-12, the most abundant isotope, formed through the triple alpha process within helium-burning stars, while the rarer carbon-13 isotope originated primarily in the hydrogen-burning shells of aging red giant stars. The ratio between these isotopes, preserved unchanged within the comet's ice matrix for billions of years, provides a direct measurement of the galactic chemical evolution that preceded the solar system's formation. Oxygen isotopes tell an even more complex story of stellar nucleosynthesis and interstellar mixing processes. The three stable isotopes of oxygen, oxygen-16, oxygen-17, and oxygen-18, formed through different nuclear pathways within different types of stars, their relative abundances reflecting the integrated history of star formation and stellar death within the local region of the galaxy. Oxygen-16 formed primarily through helium burning in massive stars, while oxygen-17 and oxygen-18 originated through hydrogen burning and explosive nucleosynthesis during supernova events. The preservation of these isotopic signatures within the molecular structure of carbon monoxide molecules represents one of the most remarkable aspects of comet chemistry. Unlike terrestrial materials, which have undergone extensive chemical processing and isotopic mixing over billions of years of geological activity, the comet's volatile compounds retain the original isotopic compositions they inherited from the interstellar medium that gave birth to the solar system. Each molecule becomes a time capsule, preserving nuclear fingerprints that date to epochs when the galaxy was younger and stellar populations had different characteristics. The nitrogen isotopes present in both molecular nitrogen and ammonia carry information about nucleosynthesis processes that remain poorly understood despite decades of theoretical and observational study. Nitrogen-14, the dominant isotope, forms through complex nuclear reaction chains within massive stars, while nitrogen-15 originates primarily through nova explosions on the surfaces of white dwarf stars. The ratio between these isotopes varies significantly among different stellar populations and galactic regions, making nitrogen isotopic compositions valuable chasers of cosmic chemical evolution. The scientific challenge lies in interpreting these isotopic measurements to reconstruct the chemical history of the molecular cloud from which the solar system formed. The observed ratios represent averages over multiple stellar sources and mixing processes that operated over millions of years before the solar nebula's collapse. Each isotopic signature tells part of the story, but the complete narrative requires understanding the complex interplay between stellar nucleosynthesis, supernova shock waves, stellar winds, and interstellar chemistry that shape the chemical composition of the pre-solar molecular cloud. Computer models of galactic chemical evolution provide frameworks for interpreting these isotopic observations, but the models depend critically on assumptions about stellar evolution, supernova rates, and interstellar mixing processes that remain uncertain. The isotopic data from 3I Atlas provide new constraints on these models, helping to refine understanding of the processes that govern element formation and distribution throughout the galaxy. The temporal variations in isotopic compositions observed as different volatile reservoirs within the comet become active provide additional insights into the spatial and temporal heterogeneity of the early solar system. Materials released during the early phases of outgassing show isotopic signatures that differ subtly from those released later, suggesting that the comet nucleus preserves chemical gradients that reflect conditions during its original formation. These gradients may record variations in the isotopic composition of the solar nebula as it evolved through gravitational collapse and thermal processing. The preservation of isotopic heterogeneity within the comet nucleus challenges models that assume thorough mixing of materials during planetary formation processes. The survival of isotopic variations over billion-year timescales indicates that mixing processes within the early solar system were less efficient than previously thought, allowing preservation of chemical signatures that record local conditions rather than system-wide averages. Rare isotopes provide particularly valuable information about exotic nucleosynthesis processes that occur only under extreme conditions. The detection of oxygen-17 in carbon monoxide molecules, for example, requires formation through nuclear reactions that operate efficiently only in the hydrogen-burning shells of massive stars. The abundance of this rare isotope provides constraints on the stellar populations that contributed material to the pre-solar molecular cloud. The noble gas isotopes trapped within the comet nucleus represent the ultimate in chemical inertness and isotopic preservation. These elements form no chemical bonds under the conditions that exist within comet nuclei, so their isotopic compositions reflect purely nuclear processes rather than chemical fractionation. The xenon isotope ratios measured in 3I Atlas show signatures of neutron capture processes that operated within the interiors of massive stars, providing direct evidence for the stellar sources that contributed heavy elements to the solar system's formation. The scientific mystery embedded in these isotopic observations lies in understanding how such pristine chemical signatures could survive the violent processes that accompanied solar system formation. The collapse of the molecular cloud, the formation of the protoplanetary disk, and the accretion of solid bodies all involved high temperatures and turbulent mixing that should have homogenized isotopic compositions. The preservation of original isotopic signatures within comet volatiles suggests that some materials avoided thermal processing and mechanical mixing during these formative processes. Laboratory studies of isotopic fractionation provide insights into the physical and chemical processes that can alter isotopic compositions during solar system formation. Temperature-dependent fractionation effects can change isotopic ratios during phase transitions and chemical reactions, while mass-dependent processes can create systematic variations that reflect the physical conditions under which materials formed or were processed. The comparison of isotopic signatures between different molecular species within the comet coma provides additional constraints on formation and preservation processes. Carbon and oxygen isotopes in carbon monoxide molecules show different patterns of variation compared to the same isotopes in water vapor, suggesting that these compounds originated from different source reservoirs or experienced different processing histories during solar system formation. The implications of isotopic preservation within 3I Atlas extend beyond the specific case of this individual comet to broader questions about the chemical inheritance received by the solar system from previous stellar generations. If pristine isotopic signatures can be preserved within solid bodies over geological timescales, similar chemical archives may exist within asteroids, meteorites, and the interiors of planets, providing windows into galactic chemical evolution that spans billions of years. The ongoing loss of isotopically pristine materials through outgassing represents an irreversible experiment in cosmic archaeology. Each departing molecule carries away a piece of evidence about nuclear processes that occurred billions of years ago in stellar environments that no longer exist. The information content of these molecules cannot be recovered once they disperse into the interplanetary medium, making the current observations of 3I Atlas a unique and time-limited opportunity to study the chemical legacy of stellar nucleosynthesis. The isotopic library contained within the comet nucleus represents more than just a collection of nuclear data. It provides a direct link to the cosmic processes that created the chemical elements essential for rocky planets and life itself. The calcium atoms in terrestrial bones, the iron in blood, the carbon in organic molecules all trace their origins to nuclear furnaces within ancient stars, their isotopic signatures carrying the memory of temperatures and pressures that existed billions of years ago in stellar cores that have long since collapsed or exploded. As the isotopically rich gases continue to stream away from the comet nucleus, they carry with them the chemical testimony of cosmic evolution, the molecular witnesses to stellar birth and death that shape the chemical composition of our corner of the galaxy. Each escaping molecule represents both a scientific revelation and a cosmic farewell, information about the universe's chemical history delivered across billions of years of time, then lost forever as the messenger disperses into the cosmic background. Its story told, but its substance irretrievably scattered across the vastness of interplanetary space. The gradual convergence of observational evidence, theoretical modelling, and laboratory analysis begins to reveal the extraordinary nature of 3I Atlas as more than just an unusually active comet, but as a pristine archive of solar system formation processes that operated under conditions fundamentally different from those assumed in standard models of planetary accretion. Each new spectrum, each refined isotopic measurement, each detailed image of the nucleus and coma contributes another piece to a scientific puzzle that challenges decades of established theory and forces astronomers to reconsider their understanding of how solid bodies formed and evolved in the outer regions of the early solar nebula. The chemical inventory preserved within the comet nucleus appears to represent materials that accreted under temperature and pressure conditions that existed only during the earliest phases of solar system formation, before the protoplanetary disk had undergone the thermal and dynamical evolution that characterizes later stages of planetary accretion. The hypervolatile compounds, exotic isotopic signatures, and complex organic molecules detected in the outgassing coma all point towards a formation in a region of the solar nebula that possessed chemical characteristics not seen in any other population of small solar system bodies. Computer simulations of early solar system dynamics provide frameworks for understanding how such pristine materials could have been preserved within a comet nucleus. The models suggest that 3I Atlas formed during a brief window of opportunity when the outer regions of the protoplanetary disk retained the chemical composition and thermal structure inherited from the original molecular cloud. Before stellar radiation and gravitational instabilities began to modify the disk's properties through heating, mixing, and material transport processes, the timing of this formation window appears critical to understanding the comet's unusual properties. Bodies that formed too early in solar system history would have incorporated materials that had not yet undergone the chemical processing necessary to create complex organic compounds and isotopic fractionation signatures. Objects that formed too late would have accreted from materials that had been thermally processed and chemically homogenized by disk evolution processes, losing the pristine signatures that make 3I Atlas so scientifically valuable. The spatial location of the comet's formation region within the early solar system emerges as another crucial factor in determining its final composition. Standard model place comet formation in the region beyond Neptune's current orbit, where temperatures were low enough to allow the condensation of water ice and other volatile compounds, yet the chemical evidence from 3I Atlas suggests formation in an even more distant region, possibly in the transition zone between the gravitationally bound protoplanetary disk and the surrounding molecular cloud material. This formation environment would have provided access to materials that retained more of their original interstellar characteristics, including isotopic compositions and molecular structures that had not been significantly modified by solar nebula processes. The comet becomes not just a sample of early solar system materials, but a preserved fragment of the interstellar medium that gave birth to the solar system, carrying within its frozen structure direct chemical evidence for the galactic processes that preceded planetary formation. The preservation mechanism that maintained this chemical archive for 4 billion years appears to involve multiple layers of protection operating at different physical scales. At the molecular level, incorporation into clathrate structures and amorphous ice matrices prevented chemical alteration and isotopic exchange. At larger scales, the comet's porous structure and low thermal conductivity provided insulation that prevented thermal processing even during brief periods of solar heating during its journey to the Oort cloud. The ejection process that sent the comet into its distant orbit may have provided additional protection by removing it from the inner solar system before significant thermal processing could occur. Computer simulations suggest that most objects scattered by planetary gravitational encounters undergo substantial heating during their departure trajectory. Yet, 3I Atlas appears to have avoided such thermal modification. The specific dynamics of its ejection may have involved particularly rapid acceleration that minimized thermal processing, or passage through regions of the early solar system where temperatures remained exceptionally low. The long exile in the Oort cloud provided the final stage of preservation, creating environmental conditions so stable that chemical alteration rates became negligible over geological timescales. The cosmic ray bombardment and stellar heating that gradually modified the comet's surface created protective layers that further isolated interior materials from external influences, creating preservation conditions more effective than any conceivable technological storage system. The scientific implications of this preservation story extend far beyond the specific case of 3I Atlas to fundamental questions about information storage and retrieval in natural systems. The comet demonstrates that complex chemical information can be maintained in solid form over timescales that encompass significant fractions of the universe's current age. Provided the right combination of physical and chemical conditions can be achieved and maintained, the comparison with other solar system bodies reveals the exceptional nature of the preservation achieved by 3I Atlas. Meteorites, despite originating from asteroids that formed in the inner solar system where thermal processing was more severe, show evidence for some preservation of pre-solar materials and isotopic anomalies, yet none approach the level of pristine preservation apparent in the comet's volatile inventory, which appears to retain chemical signatures that date to the molecular cloud stage of solar system formation. Planetary interiors may contain chemical archives comparable to those preserved in 3I Atlas, but accessing such materials remains far beyond current technological capability. The comet's return to the inner solar system provides a unique opportunity to study pristine materials from the solar system's formation through direct sampling of outgassed volatiles, creating a natural experiment in cosmic archaeology that reveals information otherwise locked within inaccessible planetary cores. The theoretical framework required to interpret the comet's chemical signatures draws from multiple scientific disciplines, integrating stellar nucleosynthesis theory, interstellar chemistry models, protoplanetary disk dynamics, and comet nucleus physics into a comprehensive understanding of how the information about cosmic chemical evolution can be preserved within solid bodies. The interdisciplinary nature of the research challenges traditional boundaries between different areas of astronomy and planetary science. The observational techniques developed to study 3I Atlas push the boundaries of current instrumental capability, requiring sensitivity and spectral resolution that exceed the specifications of most existing telescopes and spectrometers. The scientific return from these observations justifies the technological investment, as the information content of the comet's chemical inventory provides constraints on fundamental processes that operated during the solar system's formation. The temporal limitations of the observational window create urgency for data collection and analysis. The finite volatile inventory of the comet means that each day of outgassing represents irreversible loss of materials that cannot be recovered or replaced. The scientific community faces a race against time to extract maximum information from observations before the chemical archive is exhausted and dispersed into space. The legacy of 3I Atlas extends beyond its immediate scientific contributions to its role as a proof-of-concept demonstration that pristine materials from the solar system's formation can survive the journey through deep cosmic time. The comet establishes precedent for the existence of other chemical archives within the Oort cloud and similar reservoirs around other stars, suggesting that the universe may contain vast libraries of information about stellar and planetary formation processes waiting to be discovered and decoded. The philosophical implications of chemical preservation over cosmological timescales touch on fundamental questions about information, entropy, and the relationship between structure and meaning in natural systems. The comet's molecular library represents a rare example of increasing information content over time, as the chemical signatures that seemed random or meaningless during the solar system's formation have acquired scientific value through the development of instruments and theoretical frameworks capable of interpreting their significance. As the evidence for exceptional preservation within 3I Atlas continues to accumulate, the comet transforms from an interesting astronomical object into a unique scientific resource that provides unprecedented insights into processes that operated when the solar system was young. The slow revelation of its chemical secrets unfolds through careful observation and analysis, each measurement adding another piece to the puzzle that describes how the materials of planetary formation were assembled, processed, and preserved across the vast expanses of cosmic time. The inevitable return to darkness begins not as a single moment of cessation, but as a gradual dimming that unfolds with the same geological patience that characterized the comet's original journey outward from the sun's warmth. As 3I Atlas recedes beyond the orbit of Jupiter, moving ever more slowly against the persistent pull of solar gravity, the delicate balance between thermal input and radiative cooling shifts decisively toward the cold of interplanetary space. The outgassing that sustained the comet's activity for months continues to weaken, each passing day marking a further reduction in the volatile inventory that took billions of years to accumulate and preserve. The surface temperature of the nucleus drops below critical thresholds for the sublimation of various volatile compounds, beginning with the most exotic hypervolatile ices and progressing through carbon monoxide, molecular nitrogen, and finally water vapor as the comet's distance from the sun increases beyond 10 astronomical units. Yet the cessation of outgassing proceeds irregularly, with sporadic bursts of activity as internal reservoirs of volatile compounds find temporary pathways to the surface through this complex network of fractures and pores that riddle the nucleus interior. The spectroscopic signatures that reveal the comet's unusual chemistry begin to fade as gas production rates drop below the detection limits of even the most sensitive instruments. The carbon monoxide emissions that first announced the comet's exceptional volatile inventory disappear into the instrumental noise, their absence marking the end of a molecular conversation that connected human observers to chemical processes that occurred during the solar system's birth. The isotopic ratios that carried information about stellar nucleosynthesis and galactic chemical evolution become unmeasurable as the flux of departing molecules drops towards zero. The coma continues to expand even as its source of replenishment diminishes, the gases and dust ejected during the comet's active phase dispersing slowly through the vacuum of interplanetary space. The density of this expanding envelope drops exponentially with distance from the nucleus, creating a tenuous sphere of material that will eventually merge with the solar wind and interplanetary medium. Within this dispersing cloud, the molecules that once carried the chemical signatures of the comet's ancient formation history scatter in random directions, their information content lost forever to the cosmic background. The dust component of the coma provides the final visible evidence of the comet's activity, persisting longer than the gaseous emissions due to the momentum acquired during ejection from the nucleus surface. Tiny particles of ice and rock continue to scatter sunlight for weeks or months after gas production ceases, creating a gradually dimming halo that marks the comet's position against the star field. These dust grains, liberated from ice matrices that preserved them for billions of years, face their own fate of gradual destruction through cosmic ray bombardment and micrometeorite impact. The nucleus itself bears the scars of its brief return to activity, its surface altered by the sublimation processes that excavated volatile-rich regions and exposed deeper interior materials. High-resolution imaging reveals new topographic features, pits, valleys, and scarps that record the locations where outgassing was most intense. These features will persist long after the comet returns to dormancy, serving as geological records of the thermal processes that temporarily awakened the ancient wanderer from its frozen sleep. The scientific legacy of 3I Atlas begins to crystallize as astronomers compile and analyze the wealth of observational data collected during its passage through the inner solar system. Each spectrum preserves a snapshot of chemical processes that reveal themselves only briefly, creating a temporal record of molecular evolution within a warming comet nucleus. The isotopic measurements provide constraints on theoretical models of solar system formation that will influence research directions for decades to come. The theoretical implications of the comet's unusual chemistry propagate through multiple areas of planetary science and astronomy. Models of volatile distribution and preservation within the early solar system require revision to account for the extreme chemical gradients and long-term stability demonstrated by 3I Atlas. Theories of comet formation must address the specific conditions that could create and preserve such pristine chemical archives within the chaotic environment of the early outer solar system. The observational techniques developed to study the comet's exceptional properties advance the state of astronomical instrumentation and analysis methods, creating capabilities that will benefit future studies of other comets and small solar system bodies. The spectroscopic detection of hypervolatile compounds and trace isotopic species pushes the boundaries of what can be measured in astronomical objects, establishing new standards for sensitivity and precision in remote chemical analysis. The comparative planetology perspective provided by 3I Atlas enhances understanding of chemical evolution throughout the solar system by providing a reference point for pristine materials that avoided the thermal and dynamical processing experienced by most other solar system objects. The comet's chemical inventory serves as a baseline against which the evolution of planetary atmosphere, meteorite compositions, and other manifestations of solar system chemistry can be measured and interpreted. The educational impact of the comet's passage extends beyond the professional astronomical community to public understanding of solar system formation and cosmic chemical evolution. The story of an ancient ice ball carrying chemical messages across billions of years of time captures imagination while illustrating fundamental scientific concepts about stellar nucleosynthesis, planetary formation, and the preservation of information in natural systems. The technological spin-offs from comet research contribute to broader scientific and engineering capabilities, as the instrumental requirements for detecting and analyzing faint spectroscopic signatures drive advances in detector technology, signal processing algorithms, and data analysis techniques. These developments find applications in fields ranging from atmospheric monitoring to medical diagnostics, illustrating the interconnectedness of basic research and technological innovation. The philosophical questions raised by the comet's preservation of chemical information over cosmological timescales touch on fundamental issues about the relationship between information and entropy in natural systems. The comet demonstrates that increasing complexity and information content can emerge from apparently random processes, given sufficient time and appropriate boundary conditions. This perspective influences thinking about the emergence of complexity in biological systems and the potential for information preservation in other astronomical contexts. The international collaborative effort required to fully characterize 3I Atlas during its brief period of accessibility demonstrates the benefits of coordinated scientific research across institutional and national boundaries. The sharing of observational data, theoretical insights, and analytical techniques among research groups worldwide accelerates the pace of discovery and ensures that the maximum scientific value is extracted from the rare opportunity to study pristine solar system materials. The economic value of the scientific knowledge gained from studying 3I Atlas remains difficult to quantify. As basic research into solar system formation processes rarely produces immediate commercial applications, yet the fundamental understanding of planetary formation and chemical evolution contributes to the knowledge base that underlies space exploration, resource utilization, and the search for life in other planetary systems. The investment in comet research represents a contribution to humanity's long-term scientific and technological capabilities. As the comet continues its slow recession toward the outer solar system, carrying within its diminished nucleus the remaining fragments of its chemical archive, it begins the transition back to dormancy that will characterize most of its next orbital period. The thermal wave that penetrated inward during its approach to the Sun will gradually dissipate, allowing interior temperatures to return to the extreme cold that preserved volatile compounds for the past 4 billion years. The orbital mechanics that govern the comet's future trajectory ensure that it will not return to the inner solar system for several million years, by which time human civilization will have evolved beyond recognition, and the technological capability to study returning comets will have advanced immeasurably. The scientific opportunity represented by 3I Atlas occurs only once in the span of many human generations, making the current observations a unique window into processes that operated during the solar system's youth. The comet's journey back toward the Oort cloud will unfold with the same stately pace that characterized its original exile billions of years ago. As it moves farther from the Sun, the influence of stellar perturbations and galactic tides will once again begin to dominate over solar gravity, subjecting the comet to the complex dynamical environment that governs long-term orbital evolution in the outer solar system. The cosmic silence returns gradually, like evening settling over an ancient landscape. As 3i Atlas drifts beyond the reach of solar warmth and human observation, the comet's voice, briefly raised in molecular song during its passage through the inner solar system, fades into the quiet whisper of interplanetary space. The chemical messages that spoke across billions of years disperse into the darkness, their information content scattered among the atoms and molecules that compose the thin medium between the worlds. In the growing darkness beyond Jupiter's orbit, the comet nucleus cools toward the temperatures that will define its existence for the next million years. The exotic ices that survived 4 billion years of preservation have mostly departed, their molecular structures dissolved into the expanding vacuum of space. Yet within the deepest regions of the nucleus, protected by layers of dust and less volatile ice, perhaps some chemical archives remain, waiting for another gravitational encounter to redirect the wanderer back toward the sun. The scars left by sublimation will heal slowly as cosmic dust settles into the excavated regions and space weathering gradually darkens the exposed surfaces. The comet will tumble through the outer solar system, its rotation slowly damped by tidal forces and radiation pressure, until it achieves the stable orientation that characterized its long exile in the Oort cloud. The surface features created during its brief awakening will persist as geological memories of thermal processes that operated for mere moments in the comet's billion-year lifetime. The scientific data collected during the comet's passage continues to flow through research institutions around the world, each measurement a fragment of information about times when the solar system was young and the future remained unwritten. Theoretical models evolved to accommodate the new understanding of volatile preservation and chemical evolution, while observational techniques advanced to capture ever fainter signatures from increasingly distant objects. Somewhere in the Oort cloud, other ancient wanderers drift in orbits that may someday bring them back to the inner solar system, carrying their own chemical libraries and isotopic archives. Each potential visitor represents another opportunity to peer into the past, to read molecular messages that date to epochs before Earth existed in recognizable form. The population of preserved time capsules extends like a vast spherical library around the sun, waiting for gravitational encounters to wake them from their frozen dreams. The comet continues outward, growing smaller and dimmer against the star field. Its brief conversation with human civilization concluded, but not forgotten. In the data archives and theoretical frameworks that preserve the memory of its chemical revelations, 3i Atlas achieves a different kind of immortality. Its molecular messages translated into human understanding and preserved in the growing library of cosmic knowledge. The darkness deepens around the receding wanderer as it returns to the realm of eternal twilight, carrying within its frozen heart whatever chemical secrets survived the awakening. The universe expands around it, vast and patient, while the comet settles back into the rhythm of geological time that measures change in millions of years, rather than human generations. In the perfect quiet of interplanetary space, where sound cannot travel, and light arrives only as isolated photons from distant stars. The comet begins again the patient waiting that characterizes its existence. The thermal energy that briefly awakened its volatile inventory dissipates into the cosmic background, and the molecular motion that drove sublimation and outgassing slows toward the quantum mechanical minimum that defines absolute zero skis. The story concludes not with drama or resolution, but with the gentle return to silence that governs most of cosmic history. The comet drifts onward through the darkness, a messenger whose message has been delivered, an archive whose contents have been partially read, a wanderer whose brief visit illuminated both the chemical heritage of the solar system and the patient persistence of information across the vastness of deep time.